Okay, I think this got us. This got us. Psychology professor, not an English professor. Okay, so today we're just going to go through. I'm thinking about sort of moving forward. So we're going to move through some of this stuff pretty quickly in terms of basic descriptive statistics. Is hoping that it's a lot of review, but just really want to make sure that we touch base so that you're understanding really what's going on with some of this stuff. Okay, so we stopped up or finished up with levels of measurement. Again, starts to become important. It gets really tricky as you start to break things down and think about like, okay, like is this actually a continuous scale, or is it actually an ordinal scale that we're just pretending is going to be continuous? Remember that if we're going to say that something is actually continuous, it means that all values are equally spaced and that the value can take on an infinite number of values in between anything, right? That's the quality of a true continuous scale. So a lot of the things you think about continuous, like, oh, the number of drinks I have in a month, right? So maybe we think about that continuous. And depending on how we're measuring it, it could be continuous if we're thinking about this in terms of volume, because then yes, that can take on any value. But if it's number of drinks, then that starts to become different, right? That's probably going to be an ordinal count variable because some drinks are bigger than others and some drinks have more alcohol than others. I wouldn't say that sort of, particularly craft beer today, right? If I have 2 beers, that 2 beers isn't definitely necessarily the same amount of someone else's 2 beers, depending on what they're drinking, right? So as we start to sort of work with our constructs, really starting to think, what am I trying to measure? What's the observable that I'm capturing? And so then how does this work, right? A lot of times we treat those ordinal scales as continuous, and a lot of times that's fine, so long as we know what we're doing and we're doing it sort of aware of how we're treating this. Okay. All right. Yeah.
So can something be ordinal if it uses like half or like decimals too? So like if it's like 1.5 for drinks.
I mean, yeah, I would still call that an ordinal scale. Like sort of the thing here with a true continuous scale, right, is the idea that each unit is equal distance for, like, it's all the same, right? And even number of drinks, I would say, is still a count variable because we're saying number of, and even if we cut it in half, I'd still say that's an ordinal variable because it's not meeting the true definition of an interval scale, or in this case, a ratio, because if I have 0 drinks, that's a true 0. It means the absence of that thing, right? So again, with this assignment, right, I'm having you do some like thinking about like what is the construct we're kind of trying to measure, and then how are we sort of measuring this? And sometimes it depends a little bit on, if I were to do it this way, we'd probably think about it this way. If I were to do it this way, we'd think about it this way, right? And so thinking about intent and sort of at a higher level, like what are we trying to capture? What are we actually measuring? And do those things line up? Like that's such an important skill. We take it for granted. We don't think about it. But in terms of evaluating research, it's super important, right? Like, okay, you said you measured this, but you actually didn't. You measured this other thing, and it's probably close. But if we're being technical about things, you kind of missed it. Mustache hair in my mouth. Yeah. Yeah.
Yourself. But so if we think about like number of drinks in terms of like volume, you were saying that would be like whereas like number of drinks.
Sure. But if I was you're thinking about this, if your intent is to measure alcohol intake by volume, and you're measuring it by number of drinks, those are different measures.
Yeah.
Right. And so if you're in Allison's lab and it literally is volume of alcohol by this percentage, and so it's measured out and that's what you're doing, then that's a continuous variable, right? But if we're doing survey research and we're asking people to report the number of drinks that they're having, that's just a rough approximation, right? Because I don't know, this drink could, and you could say, well, standard drinks maybe getting on a little bit more, but it starts to, then the unit is drink, right? And so we start to get into, and so just thinking carefully, and sometimes you can kind of get turned around. You're like, well, actually kind of ambiguous on how this stuff comes in. And that's a fine answer because a lot of the times it is, right? So again, one of the things I want you guys to be thinking about this in a deep way. And sometimes you may come up with an answer that I didn't come up with. But if you say like, this is wise, sort of put it this way, then I'm like, fair enough. I might not 100% agree with it, but like if your justification is sound, that's now sometimes you can say like, well, I don't want to have like sort of splitting hairs type of a thing. Well, if you think about it this way, like, well, that's not what the question was asking. But I mean, thinking about very few things that are so concrete that everybody's universally going to agree on things. So I just want you thinking carefully about some of this stuff. Yeah.
Sorry, this is my last question for now. So if there's a true zero, it can still be ordinal, even if it's.
Oh yeah. So the true zero, like I can have like, how many kids do you have? This is another one of those things that's an ordinal scale, right? It's a count variable. We say, oh, the average person has 2.5 kids. 0.5 kids that's not a real thing, right? And when we get into interpreting means, this is actually a thing, right? Like if I'm using the mean as my measure of central tendency, technically I should only be using that on continuous data, because if I'm using it on ordinal data, right, like how many cars, how many vehicles does the average person have? Like, well, they have 1.5, 1.6 vehicles. 0.6 vehicles, that's not a real thing. It's not a construct. Now we can talk about it, but we should probably know that what we're talking about is not a real thing, and it's technically misapplication of the mean, right? Probably we would probably be thinking of probably a median or mode as the choice there, So we can do that, and we sort of use this. And again, I'm not saying that you can't or you shouldn't or it's wrong. I'm just saying I'm advocating for knowing what you're doing and understanding the limitations of it. Does that help?
Yes.
Cool. All right. Anything else? All right, cool. So central tendency. Central tendency, pretty standard concept. It's just sort of trying to find some score, some metric that's best capturing sort of the middle part of a distribution, okay? And again, what we're doing when we're looking about this, what we're actually thinking about is trying to find the single score that's most typical or representative, right? When we're grabbing means, medians, and stuff, we're saying this is the thing that best captures, in general, or most commonly, what's going on within this distribution, okay? And this is super, super important. Like, we're just going to be working on central tendency this whole semester. It's all about means-based comparisons. It's like, how does X thing relate to this thing, okay? Problem is we don't have one single option, right? We got a number of different options in terms of central tendency. So, Emily, where's the center of this distribution right here? 100. Yeah. Why'd you think that? Yeah, we've got a nice bell-shaped curve, right, where the peak is right there at 100. Pretty straightforward, right? Sam, what about this one? Where's the center of this distribution? Somewhere between 0 and 1. Well, yeah, what do you say 0 and 1? A little bit skewed, right? What would you say, like 1.2? Would that be kind of in the middle?
No, I wouldn't,
Maybe, right? So it starts to get a little bit more difficult, right? We've got this skew thing there. And so definitely most people are still bunched up around 0, but then we've got this tail going out, and it starts to become a little bit more difficult to say like, oh, this is the middle of the distribution. And again, when we're saying the middle, the most representative value across the entire set, okay? Josiah, what about this? What's my single best representative score in this distribution?
Well, depending on what kind of measure you're doing, like mean and
Yeah.
So if you're doing mode,
Yeah, this starts to get really tough, right? Again, because if we're thinking about central tendency, it's the one score that best describes this distribution. And if we take the mean, it's going to give us a value that like actually is not super common in this set, right? So this is looking at body mass. What do we likely have going on here? Yeah. Yeah, we probably have men and women in here, right? And so what we've got is probably, if we want to look through it, we say, oh, this is the average mass of this group. Well, I mean, it's body mass in grams, so it's probably not human people. Those would be very tiny people, but yeah, probably maybe a sex difference in some animal sort of culture or something along those lines, right? And so want to say, well, what do we do with this? I mean, we can calculate a mean, but that might not necessarily serve our best purpose or at all describe what's going on with our sample. Okay, so when we're going through and trying to decide what measure of central tendency is going to be best, we're generally thinking about the type of data and the shape of our distributions. Okay, these are the two considerations when we're trying to step back and think about things. Okay, the mean, everybody loves the mean. If we're talking statistics, we talk about this. The mean is the first population moment of a distribution. Population moment just means sort of characteristic. Means number one. Calculating is easy. It's just the sum of the scores divided by the number of scores, just an average. Mean, average, exact same thing. Okay. As we go through, just in case no one's told you yet, I'm never going to ask you to memorize a definition, like a mathematical definition. That's not the way applied statistics work. Matt, you're not going to find yourself in the middle of an action movie where, someone pulls out a gun and demands to know the computational equation for variance or something like that, right? Like if you need to know the computational equation for formula for variance, you just look it up, right? So I'm not interested in you memorizing formula, but I do want you to look at these formula, okay? Because they tell you a lot about exactly what's going on, right? Conceptually, you can look at these formula and say, okay, well, basically what we've got is the sum of the x's, right? That's just the total divided by the number in the sample. That's just an average, right? So with statistics, if you're having a hard time figuring things out, just looking at that formula and back, okay, literally what is going on here? They're saying sort of do this. Trust me, it will help you internalize kind of what's happening with some of this stuff. And with a mean, nice population mean, sample mean, both calculated the exact same way, no differences there, okay? Other thing we'll do sometimes is we'll have to identify a weighted mean. What we do is we find this is the total average of two samples here. We have the sum of the first set of scores plus the sum of the second set of scores over the size of the two samples together, okay? The thing to remember, and this will come up, your weighted mean is not the average of the two sample means, okay? So I can't take mean of group one, mean of group two, and average those out and get a proper weighted mean under most circumstances. Why is this? Yeah, sample size is different, right? It's a rare day where you have exactly the same number of people in group A and group B, right? If my sample size, then I've got more people in one than the other. And so I'm taking an average of 50 people and an average of 20 people and taking the two averages, basically averaging averages. And then that starts to become problematic if I'm actually looking at the total number across everything, right? Now, when will the average of the two means be equal to the weighted average? Yep, when the sample sizes are the same, right? So if both, and there are going to be cases where this comes up, like repeated measure stuff. Well, yeah, I can take the average at time one, average time two, and just shortcut that because I've got the same people sort of time one and time two. But with our between group stuff, remember, if we need to get an average for the whole sample, we can't just take average of sample one, average of sample two, and divide it by two, because we're going to get off base with that. Yeah, Teresa.
You'll find a weighted mean for more than two samples.
Yeah. And we'll end up doing that sort of as we start to get farther on down the road, when we start to calculate effect sizes and things along those lines. Where it really comes into play when we're looking at weighted variances and things like that, right? So variability in this sample and variability in this sample, why you just can't take the average of the two, because we're almost always going to be working with different sample sizes, right? And so we need to make some adjustments with some of that. So yeah, as we start to go in, and this is going to get into some second semester stuff, or sort of later on when we're doing linear contrasts, we just expand the formula and just start adding that in, and that's all we need to do. Right. Cool. So characteristics of the mean. thinking about the mean, what's nice and beautiful, and also the bane of our existence, is that every score in the distribution contributes to the mean. That means every single observation contributes to the calculation of that score. We're using all the information at our disposal to go through and calculate this descriptive statistic. So if I change a score, it's going to change the mean, right? So if I have a sample of 50 and I change one of those person's scores, it's going to change the mean. If I add a new score, it's going to change the mean. Except when? When can I add a score and it doesn't change the mean? Yeah, when it's the same value as the mean. Say I have an average of 20, sample of 100, average of 25. I add its score and the average of that score is 25, then it changes it, right? This starts to become important when you're doing applied research. I don't know how much time I spend because I'm pretty intense about sort of wanting to be specific stuff. I go through and do a bunch of stuff and then I'm like, cripes, I should have had that person in, or I should have taken that person out. Now my descriptives table is all wrong, where I mean the standard deviation. If you got a small sample, it could change it around a great deal. If you got a bigger sample, it's probably not going to move things around too much, but always recognize if I add or subtract or change something, it's going to change my mean, okay? If, however, I go through and add a constant, subtract a constant, multiplier, divide a constant by every single score, it's going to change the mean by that value, okay? And this is something that comes up all the time. We're constantly doing this in scaling issues, right? So here I'm measuring a distribution in inches, and then I go through and I measure it sort of like, oh wait, I want to calculate this in feet, okay? If I take every single score in the distribution, divide it by 12, my mean's gonna, if I take the mean of the first distribution, divide it by 12, I'm gonna get the mean of the second distribution, okay? Thinking about where we see this a lot. Let's say you put together a survey in Qualtrics, right? And you want to go through and say how long on average is it taking people to go through and do this. Qualtrics is probably going to list that in seconds. Maybe like, I don't like seconds because 346 seconds isn't an immediately intuitive amount of time for anybody. So I want to convert those to minutes. I go through and do it. I can go through, and if I have the mean in seconds, I just divide that by 12. It's going to give me the mean in minutes. It's mathematically equivalent with this, okay? Performing an arithmetic operation on every single score in the set also doesn't change the distribution. Distribution is exactly the same. It doesn't change any of the shape. Same thing. We're just going through and knowing that if I add 3, it's going to increase by every score. It's going to increase the mean by 3. If I subtract 12, it's going to increase by 12. If I multiply it by 2, it's going to multiply everything by 2. Just a scaling issue. And this starts to become important when we're doing sort of get on into structural equation modeling. You've got a bunch of different variables that are different scaled. Sometimes you can have something called an ill-scaled matrix. If like my one measure ranges from 0 to 0.5 and the other one ranges from negative 500 to 4,000, right? Probably get in there and do some rescaling thing, but it doesn't change the property of the scale at all of the distribution. Standard deviation does change.
Oh, it does?
Yes, yeah,
Oh.
yeah. So I can, let's say Teresa reports, a score on a measure, a 10-item measure. Let's say Teresa's reporting Rosenberg's self-esteem score in a publication, and she's reporting some scores. But turns out this Rosenberg's self-esteem scale should be reported as an average. And I want to compare the score in Teresa's sample to my data. I can just divide her score by 10, and that gives me the average of her score and the sort of metric that I understand, right? Problem is I don't know what the standard deviation, I can't back translate that standard deviation on that because there's different stuff going on there, okay? So for some stuff we can move back and forth, and knowing, sort of recognizing this can be helpful because I can say, okay, I don't like how Teresa reported that. I think Teresa needs to learn how to score scales consistent with everybody else. A common thing that happens, and that's not Teresa, like it happens all the time. It's kind of aggravating from an assessment standpoint, but we can go back and forth with this. But if we start looking at variability, then things get hard. Yeah.
So I thought in the book it had like the tools, so I wonder if we added like the concept that the standard deviation.
Yep, that's true.
That is true.
Yeah, that is true. So yeah, if I go through and I add, and boy, high five. We're reading the book. I don't even know what to do with myself here. Yeah, so if I go through and if I have a value and I take every score in that value and I add 5 to it, it just shifts the distribution over. It doesn't do anything. So the standard deviation is still going to be the same, right? It's just going to shift that over, right? But if I go through and I multiply or divide everything, so yeah, no, I was wrong. Technically, I can go through and take Christina's standard deviation if it's a about that. But if I multiply every value in a constant or divide every value by a constant, I can do the same thing, and the standard deviation is going to sort of switch by that amount, right? I'm trying to do the math in my head. Like, so Christina's sum and my average is functionally the equivalent of, if it's a 10-item scale, taking each one of her scores, dividing each one of those by 10, and then adding those up should get me the mean. Yeah. So yes, I was wrong. So I could derive standard deviation from Christina's measure by taking her standard deviation, dividing it by 10 if there's a 10-item scale. I think that should work.
Adding and subtracting. Standard deviation.
Yeah, it doesn't change, right? We're just kind of shifting that whole thing around a little bit. Okay, it's the same thing with centering variables, and we'll get into that next semester, right? If I want my mean value to be 0, I just subtract all values in this set by the mean, and it just shifts that over to 0, but the standard deviation remains the same. Yeah. All right. So, yeah, addition, subtraction, multiplication, division of every score doesn't change the overall shape of the distribution. Okay. Still the same thing. So we're not transforming anything. I mean, we're transforming it in terms of the scaling, but we're not changing the shape or the order of scores or how far they are apart, anything like that. Any other questions on the mean? All right, median. Okay, median is the middle score. This is the score that divides the distribution so that we have half of the scores at top, half of the scores on bottom. Calculating the median. This is a pain to do by hand. We don't hardly ever have to do this now, but sort of back in the day, this would be like, okay, I got to list everything in order. List the scores from highest and lowest, select the middle score. If I have an even number of people, we sort of look the middle pair. Sometimes you'll see this is the midpoint, so that my median is 7.5. If I have an even number of scores, 7.5 might not be a real value in there, but we're just kind of splitting the difference with median. Okay, so median is a little bit different. It's just saying this is literally the center score. Of all the scores, this was the one that came in the exact middle. Okay. Mode, this is just pretty simple, straightforward. For the most part, this is just the one with the greatest frequency. Okay. The nice thing about mode is we can use mode with any scale of measurement. Like that modal value is just the value that occurs the most times, right? So mode is actually pretty flexible. Problem is when we start to get into multimodal types of distribution, then all of a sudden it starts to become tricky. Okay. If we go back to that mass histogram, right, we saw 2 modes that were quite prominent. One was higher than the other one. So we say the mode is this, but, and then you get into discussions about major modes and minor modes and things along those lines that we really, I don't know, back in, like the 40s and 50s and stuff like that, that classic research that no one can ever replicate. Like they did a really nice job. They were doing a lot of stuff, maybe not so great, but the nice thing that they did is they did a good job of describing their data. They also had samples like 15 and stuff like that, so it got a little bit easier at the time, but sort of more attention to sort of graphing and providing information on distributions, which starts to become nice because it communicates to your reader what's going on and thinking about, then if I get weird stuff in my data, is this just something that's a nuance of my data, or is this something that other people study find the same thing? Yeah, Sam.
It's a little tricky with like visual analog scales, when scales like really fast.
Yeah. And so if I have a true continuous distribution that maybe has some kurtosis to it, where it's kind of flat, and I have like a lot of stuff that's all kind of in between there, yeah, then all of a sudden, then that mode starts to become less useful. Same thing. So if I've got a true continuous scale, then it might start to be a little bit tricky, right? But again, a lot of this starts to be, sort of be linked to the precision of our measurements, right? If I'm measuring something in inches, then maybe mode works. Inches is a measure of length, which is by definition a ratio scale. But if I record everything in inches, then I'm sort of, my resolution on that scale gets a little bit tricky. But if I've got a micrometer and sort of measuring things out, then mode might not make as much sense. Generally, in those situations, we're going to be talking about mean anyway, unless we got something crazy going on. But absolutely, yeah, thinking about for this given situation, and this is why rules of thumb are stupid. Like, oh, if it's a continuous variable, you have to use mean. Like, well, maybe or maybe not. There's other ways. You can have a continuous variable that's multimodal, and so like the mean sucks there, right? And so there's other ways of going through and talking about things. So it all depends on sort of taking a look at the data. What am I trying to achieve, and then making the best choice from there. Talking about, yeah, relative modes, major, minor mode here, right? But this is where, as you start talking about, we'll have give you lots of practice in describing distributions. Just a lot of it's just what do you see? Like, well, distribution had a multimodal distribution at 0 and 4, which were very close. Everything else was low frequency reporting on these other things. And then maybe you drop in that histogram and like, that's what it looks like. That's a nice way of going through and communicating things. Oh, glad I got this mask on. All right. So choosing our measure of central tendency, our mean, okay? This is going to be our best go for most cases, particularly the types of inferential statistics that we'll spend a lot of time working on in class, okay? Typically provides a representative value for the set. If it doesn't, we need to start thinking about the types of analyses we're running, because that means we got something that's crazy skewed or multimodal or something like that, that maybe we ought to be careful before we jump into a t-test or something along those lines. But in general, if our data are appropriate for the types of things we're often wanting to do with mean-based comparisons, the mean is generally pretty good. Every score in the distribution is contributing to the calculation of that, so no one gets left out. Everybody's weighted equally. We see greater stability in replication samples relative to the mean and the mode, or the median and the mode, because it's an average, right? It's sort of right there, and from sample to sample to sample to sample, that mean's going to jump around less than the median, right? Because the median just kind of depends on sort of where the middle is, and from sample to sample, the geographic middle of that might sort of change around quite a bit, but the mean's probably going to stay pretty standard, right? Same thing with mode, particularly with continuous data. That mode might jump around from 21 to 24 to 23 to like, it's still, but it's all kind of the same thing. We're not talking about different results. It's just this particular measure starts to move around. So the nice quality of the mean is that it tends to be fairly stable. And this is the basis for most of our inferential statistics. Okay. T-tests, ANOVAs, regression. These are all, you'll hear these all referred to as mean-based statistics because the derivation of all of our stuff is based on sort of that mean value is where that comes from. Okay. But some limitations, right? Median starts to get drug around by extreme scores, especially under what case? When do extreme scores really start dragging around our mean?
When you have like a smaller sample
Yeah,
size.
yeah. If I don't have that many people to sort of buffer that up, right? And we'll talk about this when we're doing screening. If I'm working with samples of means-based stuff like 50, 100 or something like that, and I got one screwball that's way out there, I'm going to note it. Probably my biggest concern is whether or not that's a real case or there was some sort of transcription error or something like that. Is that actually what's going on with that case more so than whether or not it's going to sort of move stuff around. But for a lot of our experimental studies, right, or clinical studies, right, Teresa, you're working with kids with autism, right? You're probably not working with 200 samples of 200 or something because, you know, those folks aren't growing on trees to just kind of pull on in, right? A lot of times I'm working with a kind of a unique population that's very hard to get a handle on. And so I don't have that many people. And so if I start to get strange, not strange, just unusual scores relative to the distribution, it can start to sway that quite a bit, okay? We can have values that don't actually exist as an observed score. If I'm using ordinal data, right, the mean might not actually be a score or something that's real. So I have to decide whether or not I'm worried about that or not. Sometimes I usually won't be, but sometimes I might. Also, if we're going to do a strict interpretation of the mean, we need to have at least interval level data, right? Because to say, here's the average value of this thing, we're saying that what's assumed there is that 2 is equally different than 3 and 2 is equally different 4 as 5 and 6 and 5 and 7, right? And we don't think about this a whole lot. We just default to the mean, but sometimes this can have consequences, right? So we in psychology, because all of our constructs are make-believe and assigned to random values to go through and measure it, and those random values are often ordinal, almost always ordinal in nature, right? But early on, we did a lot of non-parametrics. That's kind of fallen by the wayside. They've got a place, but it's sort of more of a sort of an ancient secret sort of thing that you got to go through and dig for that stuff. But turns out that the mean-based analyses, so even though we have frequent violations of the underlying assumptions, they still work out pretty good. But again, what I want for you all is if you're violating assumption, you're doing it anyway, that you at least know it and sort of are recognizing that sort of if there are consequences, kind of think through that. So pros and cons of means, okay? Pros and cons of the median. This is going to be preferable in a lot of different situations. If I've got data that's skewed or has meaningful but extreme values, okay? This is another thing when we start talking about screening our data, right? Just because I've got an outlier doesn't mean I just pitch it. Like I need to have a good reason for throwing out an outlier, right? So if we have an extreme score and it's clearly not someone like, let's say, so this isn't a good example. Look, I'm interested in income in college undergraduates, right? And I've got sort of the distribution of scores that is representative of an income of college undergraduates. And then I have someone who's reporting, you know, 120,000 a year. And I go through and find that, and it is an undergraduate, but it's someone who's a professional who's registered as an undergraduate, maybe they're retired or something like that. Is that a person that I want to keep? Is that an observation I want in the sample? Probably not, right? This person isn't representative of when I said undergraduates, what I really meant in my head was sort of undergraduates who are traditional undergraduates when this in this level. This person is not, so probably going to go through and get rid of that person, right? But Sam, do you do substance stuff?
I do.
You okay? Yeah. So if I'm looking at, let's say, cocaine use in high schoolers or something like that, right? I might come up with a couple of outliers in there, right? But do I want to get rid of those folks?
Depends, I think, because if with self-report data, it's kind of tricky. Like,
Yeah.
I was thinking about this, like if you're like, how many drinks per week do you consume, and someone puts like 200, like
Yeah.
you know that's just not possible.
Right.
But I mean, if it is like a higher number, like for your example, if it is higher, you probably do want to keep it.
Yeah. Because a lot of times those are the people we're interested in, right?
Yeah.
Like we don't wish there were more people because that's a bad behavior to engage in. But for the purposes of my research, it would be nice to get representation for those folks, right? Now, if we want to use mean, we can do smoothing techniques and things along those lines. But then that's taking this person with extreme behavior and pulling them in, right? And so a lot of times these extreme values are the people we're most interested in, right? And so we don't want to just go chopping them out. So median-based statistics can sometimes be a nice option here. Okay. So again, when we're thinking about for our skewed data, anytime we look at skewed data, mean, median, and mode are just generally going to fall in this situation. Median is going to be right in the center. Mean's going to be on one side, mode's going to be on the other. And so this is why when we're talking about using skewed data, that median really is probably our best measure of central tendency, right? We're going to have more people to one side of it because that's the modal value. And then the mean is going to be on the other side because we've got that tail dragging out there. That median ends up being a nice middle value for this, okay? So again, something like this, what am I looking at? I don't know, something, but maybe that I've got a small number of people and that 120 score is actually someone who's actually high and I want to keep in there. This is where our median-based statistics start to become more relevant. Okay. If I have analyses with censored data, does someone know what censored data are? Yeah. Matt.
So it's when you only have partial information about a score.
Yeah.
Because it's either a ceiling or floor effect usually.
Exactly, right? So here we've got how many miles a day do you drive, right? And what we've done, miles a day. What level of measurement is miles a day? Yeah, specifically what type of continuous variable? Ratio, perfect. Yeah, exactly, right? And so here we might have a discrepancy between our construct as we think about it and the actual measurement, right? Here what we've done is, let's say we just have a checklist where we say 0 to 9, 10 to 19, 20 to 29, 30 to 39, 10-unit intervals, okay? So my construct is continuous and is consistent with the ratio scale. What's my measurement? Emily? How have I, if this is literally how I've measured it, not how I've been things, what is this? Yeah, it's ordinal, right? I have equal values, sort of, well, any given score in this isn't necessarily equal apart from sort of one and up above in it, but I've taken something that conceptually is a continuous ratio, but my observable that I've captured is an ordinal scale, right? And so needing to think about the difference between the construct as I've conceptualizing it versus the how I've actually measured it, right? But you'll notice that here we have a small number of people who we just say 100 and over, right? Well, that could be 101 or it could be 500, right? We don't know. It's just kind of a sort of up. So you're actually right, Matt. That's ceiling and floor effect here. Can I calculate a median on, or excuse me, a mean on this? Nope, I don't have enough information to do that, but I can calculate a median, right? So I can say, all right, well, those three folks, I don't know exactly how many miles they drive, but they're there. And what I can do is start counting in, and then I find the center, and now I have a median, and I'm good to go, right? So our censored data, we can go through, use our median, it's nice. And our data that are, okay. Technically, if I have some measure where there's not equally spaced intervals, right? As we talked about this a little bit last time. So even if we're thinking about a multi-item personality scale, right? Where you've got for each item, it's 1, 2, 3, 4, 5. And then even we go through and take the mean of those scores. Technically, I don't know that one person's 50 and another person's score of 60, that 10-unit difference is the same as someone who has a 40 and a 50. We're still not meeting criteria for a continuous scale. We're treating it as continuous, that's probably fine, but if we're being careful and thoughtful about it, we need to recognize that we actually don't have sort of that exact distance in between, right? And so technically with ordinal scales, median is probably the better bet because we're not assuming equal intervals between values. And so we can say, here's the median value. We ignore this for the most part, but again, if we're thinking carefully about our stuff, this is an argument to be made, right? Now, this isn't saying that everybody, all psychologists should be using median-based statistics, because that would be a pain, but is knowing what we're doing and the fact that we're making the violation and sort of thinking about the potential consequences. Okay. Other thing is thinking about, and this comes up when I'm trying to think a lot, generally substance use stuff, but do other people sort of work in areas where they're often, in their area, they're often working with transforms data? Like substance alcohol use, not using transform data, you're probably going to get in trouble from reviewers because that's just what everybody is doing, right? And so it's kind of understood that that's how it goes. I think about if anybody were a cognitive person doing like reaction time task stuff, right? That's going to be always a hyper skewed distribution. That's almost always going to be some sort of log transform, right? Because you're going to have people who are very, very quick. And then as people get, like, you can't get, there's a floor to how less quick or how fast you can do it, but there's an infinite length of time that you could take to do it. Eventually we'll probably cut it off if you take too long and not thinking or sort of paying attention. But reaction time data is almost always presented in some sort of log transform, right? Yeah, Emily.
The other guys who slept 3 hours a night.
Yeah. So you get that skewed data. And so a lot of times my outcome is just a transform data score. But the thing that's important to remember, and that we don't, even though we do this all the time, is a transformation it's a nonlinear transformation, and it means different things, particularly when you start to look at associations. But in terms of looking at comparisons, a mean-based comparison of transform data is not a comparison of means, it's a transformation, or it's a comparison of medians on this, okay? Because what we find is we see these nonlinear transforms change the shape of the distribution. That's the whole point. We've got something that's crazy skewed, and we want to get it so more in line with something that is consistent with our underlying assumptions. So it changes the shape of the distribution, but it doesn't change the order, right? If I'm the 5th highest score in the raw scale and you rerun a transform, I'm still the 5th highest score in the transform scale too. It doesn't change. It changes how close and how far apart those scores are together, but in terms of rank order, nothing is changed, okay? So as a consequence of that, if I look at the median of the untransformed variable and look at the median of the transformed variable, that's still me. I'm still represented at that same point, okay? So here's audit scores. This is the alcohol measure that's generally we find to be skewed, right? And if I go through and I take a look at my raw scores here, I have a median of 3, okay? But if I go through and I run a natural log transform on those scores, right? So it's basically taking every single score, taking the natural log of every single score, and then replot that distribution. I get a median of 1.1. Okay. Someone have a calculator? Someone take the natural log of 3 for me. What's that?
Don't know how to do that.
You get
I
it?
don't know how to do it. I would try it.
It'll probably be nice if we go through doing transforms and operations and things like that.
So when I just hit 3 and then hit the 1, hit button.
Hit the LN one.
Oh, the other.
Yeah. This is my. This I
1.0.
with the reverse Polish notation. Like it's pretty fancy.
Yeah, 1.1.
1.1, right? So the median of the score that's at the median of the untransformed variable is 3, right? But if I go and find the score that it's the median at the transformed variable, it's the same person that was there. The shape of the distribution changed. This is an easier thing to deal with our mean-based statistics in terms of the distribution, but I'm still talking about the median value.
Okay, so I'm like kind of thinking about something, and you can tell me if like this isn't the right time to bring it up, but so would this change the distribution? So I know like a lot of times in substance use research, people kind of mess with their data a little bit because it won't really be significant. So then they'll put drinkers into like abstinence, like like heavy drinkers and stuff, and they'll normally have like 3 different categories. So it'll be like categorical. Is that a way that they're like messing with the distribution, or is that where this is also coming into place?
Yeah, I mean, I wouldn't think about transformations as messing with the distribution, because if done properly, you're doing it. So I've got data that are in clear violation of what the types of analyses that I want to do. And so this is an operation I can perform on these data to bring it more in line with sort of the underlying assumptions in my test, which is completely fine so long as you understand what that does to the interpretation. Okay, like this is my big beef, and this comes from my the training in my graduate program, what happens is people often get very cavalier with their transforms, right? They're just like, oh, I had significant skew. We'll talk about why that's problematic. So I just transform the hell out of everything. And then I just move forward as if I'm working with the same metric. You're not. You're working with an entirely different variable. You're working with the log transformed of PANIS scores, or the log transform of personality, or the log transform of sort of whatever, right? And you can't just pretend that you didn't do that, because it impacts the interpretation, right? And so if I'm looking at alcohol use across freshmen and seniors or something like that, and I say, okay, we've got data like this, and so I run a transformation on my audit scores and then run a t-test on the transform data. Technically what it's saying is that the median value for freshmen is higher than the median value for of seniors, okay? But we don't often see people sort of talk about that appropriately, and it can be a hard thing to get past reviewers, because reviewers also don't understand this sometimes. But technically that's what we're saying, right? You can say the mean value of log transform audit scores, then that's fine, but log transform audit scores don't have any meaning to me. I don't know what that is, right? Now what you're talking about is a little bit different thing. If I have very skewed data that's really kind of problematic, right? And so then maybe I say low drinkers, casual drinkers, and heavy drinkers, or something like that. That's perfectly fine if you want to do that, but now you recognize that maybe I've got a thing that's continuous that I've turned into a categorical variable that might be fine as a proxy, but then sort of the problem is if we have people who are kind of right on that borderline, right? So we're saying the person, if my cut is 3 drinks a week or something like that, I'm seeing the person that has 3 drinks a week is categorically different than the person that has 4 drinks a week, as opposed to treating that as a continuous variable. And we have more advanced models that specifically account for those types of data, and those are the ones that we should probably be using. But what ends up happening is, so we go through median splits and stuff like that. Like rarely is there ever a case that anybody should use a median split in this day and age. People continue to do it. There are other better options to go through and do them with the availability of increased computing power. You know, sometimes people will do it, well, if I do it the other way, then it doesn't work out. Well, now we've got an issue of sort of generalizability, and sort of like, if I have an effect that only that only shows up if I say the incantation the exact right way, then I start to worry whether or not I actually have something that's real. Does that help kind of clarify some of that? Okay. Yeah.
Sorry, I got a little lost in the example. So can I just clarify?
Yeah.
So is that median 3 the same person as median 1?
Yep.
It's
Yeah.
the same person.
Because I had a value of 3, right? I had a 3 on the audit, right? That was my score. But then what they did is they went through and log transformed everybody in the sample. So now I no longer have a value of 3, I have a value of 1.1. But I'm still the middle person. Like I'm still representative of the center of the distribution, even though we log transform. Now the log transform shifted the distribution, kind of brought it into something that looks a little bit nicer for like running the analyses that I want to do, right? So that's still me standing there in the very center. Like if there's a sample of 101, there's 50 people below me, there's 50 people above me. I was 3 before, now I'm 1.1. I'm still in the same position, even though sort of people that have stretched out and clustered around in different ways around me. Asha, did you have a question?
Yeah, it was just about why we do transformations, but it's essentially to make it.
Well, not easy to read because it complicates interpretation quite a bit. But sometimes if I want to compare this group versus that group, right? But this is what my data looks like, I might start to worry about that as being too big of a violation of my underlying assumptions of my test. So, I mean, like I can do whatever I want. It's a free country. The problem is if I'm running a means-based analysis on really skewed data, I might not have a valid inferences. I might end up with an uninterpretable score, right? I mean, okay, I can say, yeah, I have evidence of a significant difference or anything like that. But if we start to scratch below the surface, you actually don't have evidence of anything because you I was when we played a basketball game by squash rules, and so who the hell knows what's going on now at this punk joint. So that's kind of the issue where transformations come in. So transformations definitely do have their place. I'm just saying they need to be used sparingly and with good reason, because if we're being careful about things, it adds a considerable amount of responsibility in terms of, okay, now what do these data mean? How do I interpret this? That we often don't do because people don't hold their feet to the fire. Okay. Other questions? All right, cool. So, yeah, so that's median stuff. So median can be useful. It's not going to be our go-to, but there are situations where that's going to be appropriate. Finally, choosing the mode. Okay, mode. If I got nominal scales, right? If I've got things like race, ethnicity, favorite cereal, preferred internet browser, right? Like these are all things that people may have strong opinions about sort of which group they're in or not in or things along those lines, but these are inherently nominal value. These are just named categories, right? So median doesn't make any sense. Mean doesn't make any sense, although you would be surprised how often people sort of do this stuff. Just because I can assign a number to something and the SPSS will give me a mean or a median value doesn't mean it means anything, right? But so for nominal scales, we should be using mode. If I have discrete ordinal data, things like counts, mode can be quite useful. It's the most frequent value that comes up. And then just using it to describe shapes, right? Say, even if I'm calculating sort of the mean of a distribution, I might say, boy, yeah, sort of modal value was this, just to communicate kind of where that most frequent value is. And so it can be used as a nice descriptor, but not many inferential statistics we're going to be using mode on because it's more of a descriptor than an actual sort of quantitative measure. Okay. Central tendency. How do people feel about central tendency? Feeling good about central tendency? Okay. Good with this? All right, cool. So now we're going to get in the good stuff. All right. So the time for joking is over. We're going from central tendency to variability. All right. This is probably one of the most important concepts that you need to have a strong understanding of as we move forward, right? You think about statistics back, oh yeah, means and so on and so forth. Means are fine, but that's like the little kid. You're getting into deep tracks here, right? Like the real sort of ins and outs of our statistical analyses, right? And this almost always comes down to variability. Okay, variability is going to be sort of broadly speaking. Variability is talking about the extent to which scores in some distribution end up being spread out or clustered together. Okay, so what is the spread of this distribution of scores? If all scores in my data set are equal, then there is no variability, right? I have a constant. I want to make sure that if you don't have no variability in your data, all your statistics are screwed, you're going to have a problem. So you want to have some variability. Sometimes that's not great. So you want differing value levels for depending on what you're trying to do, but need to have some variability in there, right? But if I've got stuff that's very, very spread out, sort of very, very, very different across the people that I've collected here, then I have a situation where I have quite a large bit of variability, right? And this is something important even in the planning phase that you should be thinking about in terms of research, right? Like, so how variable should I expect sort of this stuff to be, right? So again, go back to thinking about college undergraduates, true college undergraduates, right? If I'm thinking about income, in the grand scheme of income, are we like to have a lot of variability or not a lot of variability in undergraduate income? No, I'm talking about here in, yeah, probably not a lot of variability. Now there's going to be some variability, like some people are going to sort of have sort of different levels of income, but it's going to be pretty tight, right? If we start thinking about extroversion, though, across undergraduates, how much variability are we going to get there? a ton. We're going to get the whole spectrum. We're going to get people who are extremely introverted, very, very low on that extroversion dimension, to people who are out there all the time, right? And so thinking about our data, not in terms of what's the average level, but how much are people differently spread out, starts to become a really interesting and important some stuff.
I think I know that answer, but just to clarify, I'm assuming that the degree of variability comes the same to like age throughout the entire US. You know, from 1 to 100. So a lot of variability in study, but then compared to income, I think that's differences in needs. So I'm assuming that variability goes like independently study per study.
Well, it's what you're Mark talking about is a scaling issue, right? In that sort of dollar amounts sort of change sort of vastly. There's sort of an infinite on the upper end of things from 0 to as far as you can go, right? Like I have a damn rocket that I decided to shoot me into space with just for the hey ho heck of it, right? So yeah, income is probably going to be quite variable, but it's all kind of relative, right? And so, and this is why when we get into, is that Elizabeth? Okay, this is a nice sort of jump into kind of the next thing, is because when we start thinking about different metrics of variability, sometimes they can tell us quite a lot, and sometimes, even though they're valuable statistically, they don't give us much information, right? And so if I have something that's measured on a 0 to 1 scale, and I say, oh, the standard deviation of this is, or sort of, or let's say, never mind, let's go, did you say here's a standard, this variable has a standard deviation of 0.3, and this one has a standard deviation of 50. Which one of those sets has more variability? I don't know, because it all depends on the scaling, right? If I've got a scale that runs from 0 to 100, standard deviation of 50 is quite a bit, right? But if I'm talking about standard deviation of income in people in the US is 50, that's obviously not a real thing, but what we know about income, that would be an infinitely small variability, right? And so same thing, it depends on the scale of what we've got going on, right? Now, it also depends on my sample, right? So if I go through and I look at, okay, well, let's stay with income. If I look at variability of family income among college undergraduates, I'm going to have some variability. But if my population isn't college undergraduates, it's all 18-year-olds in the US. Now, all of a sudden, my variability on that has gotten orders of magnitude larger, right? Because what I'm pulling for in undergraduate, I don't recognize it, but by definition, kind of a privileged group of individuals who've been able to sort of access higher education. That's probably related to family income and status in some direction, in some way, right? And so probably I'm going to have less variability on that than if I'm looking at all 18-year-old kids in the US, right? So it really depends on I can't compare variability sort of measure to measure because there's context stuff there, but even sample to sample depends on who your population is and who you've drawn it from. That help? Okay, cool. All right. So thinking about our, sort of going back here. So remembering that our metrics of variability, this is describing our data in terms of distance. It's a distance measure, right? How far or close are things apart? If we're thinking carefully about this, these are measures that tell us how much distance to expect between any two randomly generated scores, or what distance to expect between some sort of middle score and sort of any average score that we go through and pull, right? So again, thinking about variability as a metric of distance. And as we start to get into some ANOVA types of models and some t-test stuff, our variability tells us how representative we can expect that measure of central tendency to be for the sample, okay? Essentially, this is telling us how much error to expect. So if I've got a sample and let's say mean is 20 and standard deviation is 5, right? And then I have another sample where the mean is 20 and the standard deviation is 15. For what I'm measuring, which one of those samples has more error in it? the 15, right? So if you hold the, again, I don't know, there's a lot of talk being held at gunpoint over statistics, which seems an implausible scenario. But like if Josiah comes up, sort of holds me up and says, okay, like what's the average? So I randomly grab someone out of this sample. What's their value? Josiah, what's my best guess?
What's the what? Sorry.
What's my best guess? If you have someone holding it that you're holding in your hand, you say, I've pulled this one person from this sample. What's your best guess in terms of the value of this person? What's my best guess? The mean, yeah. Mathematically, it's the mean. Every time you ask me that, I'm going to guess the mean, right? Am I more confident if I'm guessing from a sample that has a standard deviation of 5 or a standard deviation of 15? 5, right? Because there's less error in that. Like sort of everybody's whatever my measurement is, it tends to be more tight and clustered in that section, in that sample than in the one with 15. And 15, I'm going to keep each time I'm going to give you the same answer with much more trepidation in the sample with the standard deviation of 15 than of 5, right? Because it's telling me on average how much error do I have. Like I'm going to guess this. I'm always going to guess the mean. But how much variability do we have around that, right? So this is an important concept as we start to get on into our t-tests and our ANOVAs and stuff like that, thinking about variability of a group, right? So everybody in the group, I'm saying this is the group. They all are going to be the same. So what's the expected score for this variable? It's going to be the mean. But then that variability starts to tell us how much sort of error I have in terms of that estimate. Because I'm going to be right rarely, mostly wrong, but how wrong am I going to be?
Can you have variability also in like review papers, so like a systematic review analysis or something?
What's this now?
Like, can you have variability in like review papers too, instead of just
What do you mean? Yeah, help me explain what you mean about
like
variability in a review study.
like I'm just trying to think like when you're looking at all of the scores together, do you look at the variability? Maybe I'm never mind actually.
Oh, so if you're looking at say means and standard deviations across a set of papers.
Yeah,
And
but
you're
like
saying-
several, because like you would report each one for like each study.
Yeah.
And then look at I was just wondering if it's something that can only be done with like empirical studies, or if it's something that can also be done.
Well, I mean, you're thinking about variability as a concept, then yeah, absolutely, you're going to pull information from this, right? And so if I'm looking at, and I've reviewed papers, right, where I'm looking at this, like say a meta-analysis or something like that, right? So they've got a nice sort of effect size plot where they've got each individual study and sort of where the effect size is, and then the confidence interval around those. Let's see, maybe this one that has way out there that's looking like a super huge treatment effect, then it's got a confidence interval about like that big, right? That probably tells me that they had 6 people in that study and they happened to get something that was really large. But really what I should infer from that is the effect size for whatever that did. Population effect could be anywhere from 0 to insanely large, right? Which basically tells me nothing, right? So if I again, Emily, if I say, hey, Emily, when are you going to get me those notes back? You're like, well, interval anywhere from tomorrow to next year, right? Does that tell me anything about how well you're going to, or when you're planning to get that to me? No, it's way too big, right? Don't do that. That would be a bad situation. But like thinking about, so as we start to get into interval estimates, yeah, sure, our point estimate is fine, but what's the precision on that, right? And so as I'm going through, if I'm looking at studies and they reported means and standard deviations, and I notice some studies are starting to have like something that's noticeably larger than the other ones, I might start to wonder what's going on with that study. Right now, we're going to see things jump around, to some extent, but the sample that they drew from that group might be noticeably different than others. It can start to tell us something about the phenomena of interest. Like that's a thing we keep coming back to, is all of this stuff, we're just trying to learn something about and understand something about some phenomena of interest, right? So for example, if so in my area, trauma, PTSD types of stuff, and I'm looking at, say, mean PCL scores and sort of variability across those, I might see a lot of sort of high variability, high variability, high variability, really low variability, really low variability, high variability, low variability. You clinical folks, what might I be picking up in terms of sort of the variability there? And this isn't a trauma thing. This is any sort of clinical study. Yeah, let's say I'm sort of looking at studies, and studies just reporting means and standard deviations from sort of PTSD scores or depression scores or ADHD scores or any other such thing, right? And I'm saying that some have very, very lot of so it's all the same measure, right? Some have really, really high variability and some have very, very low variability. What might be going on? Sampling, what specifically about the sampling issue?
If someone were having really high variability,
Yeah. Yeah, exactly. For me in trauma focused stuff, what I'm starting to suspect is those are probably those are either help seeking samples or maybe military VA samples. Because what you see is if people are coming in for a PTSD study at a VA, they're generally people who are sort of quite high. And so they're all kind of sort of here, right? Versus if we're doing an undergrad study, we're bringing people there, then we're going to have big variability, right? And so what we've got is sort of a systematic difference that's probably going to be reflected in the mean because the clinical sample is going to be higher than the sort of the just general pop sample, right? But also noticing that we get a lot more variability. Just because they have a low mean doesn't mean that not everybody who we bring in who's an undergrad is, you know, just killing it, right? Like, oh, hey, I experienced trauma, but I'm functioning fine. A lot of them are, most of them are, but there's still going to be some people who are quite high in terms of their scores, all the way those people who've been wonderfully resilient and are doing good, right? But if I go through and I pull a clinical sample, people who are actually seeking treatment for, those folks are going to be on average much higher and probably less variability because you're not going to have people trying to seek treatment for trauma if they're generally functioning pretty well, right? So just thinking about looking at these scores and then thinking to yourself, what does this mean about the construct that I'm trying to sort of understand? It's yeah, if we use thinking carefully, sort of what does this literally mean? It starts to tell you more about the construct, which is what we should always be doing with analyses, as opposed to just worrying about sort of what a p-value is, right? Yeah.
like a tough thing for clinical anyway too, because like getting like a clinical population, to generalize that clinical population is one of the convenience in doing like, for example, it's super important, but that is a problem for others.
Yeah, well, and it also starts to become problematic too, is because anybody who's had a little bit of background, if I start to have less variability, what does that do to my correlations and the strength of my associations? Yeah, it kills it, right? And so, you know, what I might find is like in my undergrad sample, I think that X is related, I am reporting X is related to Y, but it's hard to find that, or that association is much attenuated in all the VA samples. Does that mean that my undergrad stuff isn't real? No, it's probably a method effect, just because if everybody's at the top end of the caps or the PCL going into stuff, then there's not much variability there, and that screws over correlations, right? So I've got an attenuated sort of an issue of attenuated range with that, right? So understanding all this stuff, we hyper focus on the mean, but really probably what we should do, and we'll bring up interesting questions, is being very aware of variability in scores and what that implies about whatever construct it is that we're interested in looking at. All right. Indices of variability have a range, okay? Range, this is just the distance between the highest and the lowest score in the distribution. A couple ways we can calculate this. We can calculate this as the highest minus the lowest score. This is asterisk. And SPSS is how SPSS is going to calculate things. You can also have the highest minus the lowest score plus one. People get in fist fights over this. It's not an important issue, and rarely, if ever, makes any difference. It's so, but one of those things. If you ever run into statistical trivia guy, will get maybe up in arms about him. You tell him to shut up because it really doesn't make any difference at all. But just different ways of going through and calculating. Josiah?
Why would you have the one?
So is it the difference between sort of this thing and this thing, or are we calculating the number of units between? It rarely makes any difference. You know, so it's just a couple. You'll see both of these. I'm just presenting them both. So if you see it, that's kind of what's going on with stuff. Limitations of the range. It's based on two values. 2 values. It doesn't matter how big your set is Range is only determined by two values. Okay, so it basically ignores everything else that's going on. And what it can start to do is it can start to give you misleading information about a distribution that has maybe a couple unusually large or unusually small scores. Okay. And because it doesn't take into account all the scores that you've gone through and collected, you've done a lot of work to collect all these scores. Range just counts too. Range doesn't care about anything other than your upper or your lower. And so you can start to get inaccurate conclusions about variability if we're just using range in a lot of situations. Basha, what's going on here? So I say my range is massive in this data set. But if you saw the histogram, what would maybe be a more accurate description of this? Yeah, so I just tell you the range, and my range on this is massive. But if you actually look at this graphical distribution, what's maybe a more balanced interpretation of what's going on in my data?
Not a lot of.
Yeah. I would say I actually have very little variability in this data. Like my data are really all kind of packed up. I've got one score off here in the end that I probably need to go through and double check to make sure that someone entered that correctly. Someone entered a 19 instead of a 9 or something like that. That's going to be my first consideration there. But even if it is a real score, it suggests that my data are far more variable than they actually are. Because in reality, everybody looks like they're ranging from about 3 to 7. And that's it. And then I got one score that's way out there, right? So thinking about how ways in which range in and of itself can start to be misleading. Okay. Range is pretty straightforward. Anybody have questions about range? All right. Additional range statistics. These are going to start to become important when we get into box and whisker plots. And we're going to work with a lot of those because they're really nice and provide a lot of good information on a lot of things. But basically, all of you clinical folks who are working with Terra right now in assessment, you're going to be working on a lot of sort of these range-based statistics, talking about quartiles. Think about median, and now you think about quartiles. These are basically scores that are certain positions in distribution. Okay, your first quartile, this defines the lowest 25% of your distribution. So basically, we take 100 scores, we go in 25, whatever the 25th score is, that's the 25th or the first quartile in this distribution. Call this the lower quartile or the 25th percentile. Saying 25% of scores are at or below this mark. Second quartile, this is the center of your distribution. This is just your median, right? This is the median. It's the value that's the top 50%, the bottom 50%. Your third quartile, this cuts off the upper 25% of your distribution, okay? This is the upper quartile, your 75th percentile, right? So these are just range-based sort of median-like statistics that are taking your set and it's taking the middle part, it's taking the lower 25, the upper 25, and just sectioning those off. Those are the cut points. Yeah.
I thought there were 4 quartiles.
No, I mean the fourth quartile is going to be sort of the top. So, yeah.
Maybe I just remembered.
Yeah. So your first quartile going to be 25th, second median, third quartile. And what we're really doing is sort of like where things start to be, we'll start talking about your first and your third quartile. That's the sort of distance between the first quartile and the third quartile. That's the middle 50% of your distribution. So this is sort of the boundaries for where the sort of center 50% of your scores are following right here. Okay. Sometimes here this referred to as the middle 50.
I just have a comment / question.
Yeah.
Isn't it kind of problematic to not take 50% of quartile 0, let's say quartile 1, that's 25%, and then the 75th percentile all the way to the 100th percentile, we're taking about 40% of that information out.
Well, look at this. So hold on to this. Yeah, that's you hit on a criticism. What we can do if we take this quartile system and apply to a normal curve, what we start to get is sort of basically some we can start to infer the number of people in a normal distribution who should fall within this middle piece of things, right? And so this graphic will go through and lay out smallest, max, and then your first, second, and third quartiles here. But the limitation here is that what we're doing with this is that we're throwing out half of the data, right? So we were saying, so the interquartile range of these data are X to X, which is good. It tells you where the half of your sample is falling in between these ranges. But the problem is, yeah, you're losing the other half of your data, and sort of you're not accounting for it in that interquartile range. Okay. Now this starts to get into a whole area of statistics. Oh, what are we calling this these days? Censored data. Censored different than like it's sort of a thing, but we're saying that what we want to do, and you'll see this, it's to my understanding, maybe a little bit more common in like biological sciences and things along those lines, where you're going to go through and you're just going to say the top 10% of scores, we're going to get rid of those. The bottom 10% of scores, we're going to get rid of those. And we're just going to have this censored set that's just taking, I'm losing 20% of my data, but what I'm saying is this 80% of the data that I have left is most characteristic of the population I'm trying to generalize to. So there could be other stuff going on at the top, high end. There could be other stuff going on at the low end. But I'm just saying I don't care about that. I'm going to pick the scores that are most representative and then moving forward with that, which there are sort of applications for this. It's not something that we see a lot in psychology because we're often working and most interested in the extremes, and you would be systematically getting rid of the people you're most interested in. But it is it's an approach that's intended to circumnavigate sort of issues with outlying values and how you deal with those and that type of thing. Yeah, Sam.
If we don't spend a lot of time on the memories.
Yeah.
Just like, how do you justify that decision? Like, is that like based on norms or like?
No, it's sample specific. It's like the 20% or is the top 10% of this sample.
It's just like 10% top and bottom.
And it depends on what the cuts are. Yeah. So I don't do, because I don't have occasion to do that. Just for the types of stuff that we do, like it wouldn't make sense. But yeah, there's a legitimate field of statistical practice where this is just kind of expected. And if you didn't do it, it would be strange, right? Like the argument would be you're trying to capitalize on weird extreme values in your set. So, but you know, the downside is like oftentimes we struggle with power all the time anyway. I'm generally not in a position to start just pitching people out just because I don't like the way they responded to stuff, you know? So this isn't something that we often do, but do know that it's out there, and so you'll run across it sometimes. Cool. All right. Let's go through and take a 10-minute break. Yeah, so let's come back. So 3:40, a couple minutes after, give you 10 minutes. I'll go through and pause this. Oops, not stop. Yeah.
I went like all summer thinking. I just said I was going to buy alcohol, like,
All right. So we'll jump back into this stuff here, talking about variability. People comfortable with quartile stuff, and again, we'll get back into this in box plots to start thinking about interpretations with this. Okay, cool. So, all right, we talked about range-based statistics, and talking about variance and standard deviation. Okay, these are going to be our most common indices of variability. These are mean-based metrics. Standard deviation, we're all familiar with standard deviation, but it starts to become helpful to think very clearly about what standard deviation is and what it means. Loosely, we can think about standard deviation and interpret this as, I mean, it's close, and it's not technically exact, but it's close enough. Thinking about your standard deviation as a measure of the average distance of any given score from the mean, or any two randomly selected scores from themselves, right? So it's saying on average, if I were to And again, Josiah's holding me up and says, hey, what's the value of this person I pulled from your sample? Mean is 20 and standard deviation is 5, right? I'm going to guess 20 every time, but I'm going to be on average about 5 points off with that, right? Across, if we keep doing this over and over and over and over and over again, on average, I'm going to be about 5 points off on all my guesses, right? Mean is still the best guess, but that standard deviation is telling me on average how far these scores are from one another, okay? So this is the standard deviation. This is what we see. Standard deviation has a lot of interpretive value. Variance, standard deviation is variance's cousin, or like little brother, maybe. I'm trying to think about, or sister. I don't need a gender variance and standard deviation. But variance is going to be the average squared distance from the mean, okay? Variance doesn't have a lot of interpretive value. I can't just be like, oh, hey, this is a variance. I'm like, oh, I got you, right? Variance is going to be essential for the calculation of our statistics. It's kind of the, variance is the person behind the person back here, right? It's sort of working in the background, the one that's actually pulling all the strings. We see standard deviation. Standard deviation is the cool kid. Everybody likes standard deviation. Variance is the one who's actually pulling the weight, doing stuff, right? But if you say, oh, this is the average squared distance from the mean, that's sort of not a super useful way to think about things. So we generally present things in terms of standard deviation. Standard deviation variance, again, so we can go directly from one to the other, and we'll often need to do this. Variance is just the square of the standard deviation. Standard deviation just the square root of the variance, right? And we'll talk about how we go through and calculate this. Yeah, Amanda.
So with your example, you were saying like these 5 points, like each 5, is that looking at like error?
Yep, exactly. It's telling us again, our mean is always sort of our best guess. Like this is the score that's representative of this sample in this set, right? But if you ask me, Josh, how confident are you that this score is actually going to be 5 that I just randomly plucked from now? I'm like next to 0. I don't know, depending on what the distribution may be, sort of depending on what things are. But I'm like, yeah, no, it's probably going to be wrong. But statistically, 5 is still the best guess. If I choose anything other than 5, I'm going to be more wrong more often than I am with 5. So, but just thinking about standard deviation on average, a randomly selected score is probably going to fall about 5 points from the mean. Now, some of them are going to be exactly on the mean because the normal distribution, that's also going to be the modal score. But a lot of times I'm going to get stuff that's way below, way above, right? And so our standard deviation is just sort of what we should expect, how wrong we should expect to be every time I guess the mean is the value for that randomly selected person. All right, so calculating variance and standard deviation. Think about like, oh, why do we need to worry about this? SPSS does it. Yep, that's true, but you need to know kind of where these numbers are coming from, particularly as you start to go on and do more advanced stuff, okay? So, and what happens is that our calculation of variance and standard deviation starts to get a little bit different depending on whether or not we're calculating a metric for a population of values versus the sample, okay? So let's say we've got here a population of 5 scores, okay? These are all the scores in the universe. This is my entire population. These 5 people are the only 5 people of this type in the entire universe. So I'm going to go through and calculate the variability here. So I take my X scores, and then what I'm going to do is I'm first going to take each score and I'm going to subtract the mean, okay? For this population of scores, my mean is 6. And so I'm going to take each one of those scores, I'm going to subtract 6, okay? This is going to give me a column of deviation scores. We're going to come back to this again and again and again and again. If I'm talking about a set of deviation scores, I'm just saying I've got a set of scores, and I've subtracted the mean. This is a deviation, okay? Then what we're going to do is we're going to take those deviation scores and we're going to square them, okay? We're going to go through and we're just going to take those to the second power. This is just sort of that score multiplied itself. And we're going to go through and we're kind of come up with a column of squared deviation scores. And then what I'm going to do is I'm going to add those squared deviation scores up. And this is going to give me my sum of squares. Your sum of squares is technically the sum of your squared deviation scores. That's all this is. Like what it is in the name. It's taking a set of deviation scores, I'm squaring them, and I'm going to just adding them up. Okay. Now, why did we go through and do that whole squaring thing? That seems to make things more complicated than it needs to be. Basha?
Because look at -5 to 1.
Yep.
Then all add up to 0.
Yep. If I just try and add up my deviation scores, by definition, I'm going to end up with 0. Okay. So it doesn't make any sense unless I'm just wanting to see if I've done this thing correctly. If I just add them up, half are going to be above, half are going to be below. By definition, I'm always going to get 0. If I get anything other than 0, I've done something wrong, right? But if I go through and square them, I start to lose in sort of direct interpretation value, but it also gets rid of that negative. And so what I can do is I can go through and I can calculate, square these, sum them up, and this is my sum of squares. The sum of my square deviation scores. Okay? Now, the important thing to realize is this sum of squares, this is just a metric of variability, okay? It's not a particularly intuitive measure, but it's a measure of how different your scores are. It's certainly not as interpretive, it doesn't have the interpretive value of standard deviation, and not even to the extent that variance does. It's just a raw sort of basic metric of variability, but it's variability nonetheless. Okay, and when we start to get into sort of more complex analyses, this sum of squares value is going to start to become important. So always recognize sum of squares. We think about this as kind of a background number, but it's still just a raw metric of variability. And so it can be used and is used for just that. Okay. So I've got my sum of squares. And then if I take a sum of squares and I divide that sum of squares by the number of observations in my population, the number of people in my population, this is going to give me my variance. Okay. And again, remember we talked about the variance as being variances equal to the average of the squared deviations from the mean, right? That's literally what it is. We're just taking that sum of squares, we're dividing by the number of people in the sample, and then I take that variance estimate, I take the square root of that, that's going to give me the standard deviation. Okay. And so at the population level, standard deviation is literally the average distance of any score, the average distance of scores from the mean of the population. And then if we go through, so this is the definitional formula. This is how if I want to go through and actually see where these numbers are coming from, and I had a spreadsheet, I can go through and do this. If I want to take a shortcut, we can use this computational formula. You'll get the exact same number. They're mathematically equivalent. Calculating your sum of squares is just the sum of your squared x value minus the square of your sum of your x over n. That's just a quicker way to get there than actually marching through all the steps. But the definitional formula kind of shows you where these values are coming from. Okay. All right. So plausibility check for our standard population standard deviation. So I've got a set of scores. My mean is 6. And so the closest value to that is 1 unit away, and the farthest is 5 units away. Amanda, what should my standard deviation be for this set of scores? Within what bounds? Yeah, within what bounds should my standard deviation fall?
Like, those are the ones.
Okay. What if I get a standard deviation of 6? Should I be concerned about that if I get a standard deviation of 6?
Looking at that, I would think so. Since
Well, yeah, I mean, like the farthest, if we think about the standard deviation as being the average distance of any score from the mean, I've got a standard deviation of 6. Farthest value away from my score from my mean is 5, right? Thinking about this as plausibility, right? Like, and this starts to become very important when we're running analyses is once I get my score, again, remember, what does this literally mean? And does this make sense? Because we'll make mistakes. I always make mistakes, right? And no one really cares if you make mistakes. We just want to go through and catch them. And most of the time, your mistakes are going to be like, because I've calculated something that's an absurd value given what I'm seeing here, right? And so I don't know what the actual standard deviation here is, but again, that Wilkinson paper, I think, is probably one of the best papers I've ever read. They say, there's no substitute for common sense. Just because I've got a program doesn't absolve me from the responsibility for saying like, have I done this correctly, right? I'll tell you what happens to me all the time. So in SPSS, and we'll talk about this, I don't like missing values, right? Because sometimes people will miss things. But what I do in my lab is if someone has missed an item, I just have the research assistants, whoever is entering data, hit 999. Because 999 is not a real value for anything. But if I'm going through and looking at 999 in our data set says that this person didn't answer it, this was a skip. And then I don't have to sort of see like a missing value and say, is that really missing? Did someone forget to enter it? It's explicitly saying this is a missing value, right? But if I forget that and I don't set SPSS up to code that, when I start running descriptives, I start to get really weird scores, right? I'm looking at that, I'm like, does that make sense? No, oftentimes it's because I'm like, oh, I got to tell SPSS that 999 means it's a missing value, not an actual number, right? So always when we get stuff, go through, take a look at it, say, does this make sense with what I know about the thing that I'm studying? And if the answer is no, or maybe not, should trigger something to go back through and start looking at stuff. Or, Elizabeth, do you?
No, it wasn't a question, I was just.
All right, yeah, and this is what this is look like in my head. Like this is what I'm doing. If I get crazy, ridiculous answers, I'm like, oh, I got a T statistic of 47. I'm like, did you do that? So there's sort of knowing kind of where we should be with stuff, right? And sort of going through and checking it. So I don't know if you care if I'm doing that to you in my head, but it happens sometimes. Okay, so if we're thinking about, so this is how we go through and calculate variance for population-based stuff. But again, if we're thinking back to why we do statistics in the first place, generally what we're trying to do is draw some conclusion about the population parameter based on a sample I've drawn, okay? Matt, do we ever know the population value of anything?
Incredibly rarely, and I'm not 100% sure we ever actually.
Yeah, exactly. It's a thing, right? Like it's something that exists out there in the universe, but it's an unknowable. Like it's a construct. It's something that I can think about as something that exists in theory, but it's not something that I actually will ever have an actual value on, right? And so we can think about, well, if I can actually never know what it is, what's the point of even worrying about it? Well, what I can do is start sort of drawing good samples, representative samples, and what I can start doing with our statistical analysis, I can start inferring something about that unknowable, right? I don't know and will never know exactly what it is, but based on if I've got good statistical methods, I can probably get pretty close and make some decent inferences about what's happening with this, okay? Again, but a lot of this is just depends on the extent to which my sample is representative, okay? Katie, if I have measurement error, does that mean that my sample is not representative?
No.
Awesome. Yes, why not?
So it just means that it could be a measure or like you're having issues with the way some, I don't know, actually, or you don't like that answer. Yeah, it could just mean that you're having issues with the measure.
Or it could mean that I just exist in the world and that's how things work, right? We're always going to have sampling error. Sampling error at its very core is just the difference between the population parameter that's unknowable and my sample statistic. There's always going to be, it's never going to be identical, right? Mathematically, if we carry this out far enough, like I'm always going to be off to some degree, right? Now, if my sample sucks and is not representative, then my sampling error gets bigger. And if my measures are garbage, my sampling error gets bigger. If my samples are tiny, then my sampling error gets bigger. But I'm always going to have sampling error there. It's the only thing it is it's just the deviation, the difference between the population parameter and the sample statistic. That's all it is. It doesn't, and it's always going to be there. So it doesn't tell me my sample is not representative. Now, I can have a non-representative sample, and then if that happens, then all my statistics go to hell because I've violated assumptions, right? But even if I do have good representative samples, the problem is when I use this formula, calculate the variability in my sample as an estimate of the variability in the population, what happens is I find that my samples from a statistical theory standpoint are systematically going to underestimate my population variability, okay? And this happens because in my sample, it's unlikely that I'm going to catch the full range of extreme values in my sample, right? And because of this, I'm going to get systematic bias. So simple example, let's think about height of undergraduates at the University of Wyoming, right? So I go through and let's say I get I set out in praxis, and our population is on campus students, right? So students on campus. So we're cutting out distance students. We're just saying students on campus. I set out in praxis and I just go through and just randomly sample people as they come through. You can get a decent sized sample, 100 students, right? And I go through and I take a look at so the mean value and their and variability. Mean is going to be fine. Mean is going to be an unbiased representation of the population, but my variability is going to be undershoot the mark. Okay. And the reason is as I'm standing out there with my random sample, my sample is probably going to come from the center. Now we're going to have, if I'm looking at height, I'm going to have students who are very, very tall and students who are very, very small. If the likelihood of me catching them whenever I'm out there, sort of grabbing people off of praxis at any one day, I'm going to miss those. And I'm going to miss those systematically because they're rare cases and they're not going on. So what we find is that if we use this population formula to calculate variability in our sample and use that as representative of the population, it's biased. It's always too small. Okay. And so what we end up is with a biased statistic. And a biased statistic is a statistic where our average value is going to systematically overestimate or underestimate the corresponding population parameter. And so mean is an unbiased statistic. My mean, even though I'm not catching the extremes, I'm probably equally not catching the super tall people as well as the super small people. And so my mean is still fine. I don't have to make any adjustment. My variabilities can be underestimated because I'm not catching those extreme samples. And so my sample statistic is going to be biased if the average value is not equal to my population parameter. The variability I'm calculating for my sample, if I'm using the population formula, is going to be systematically smaller than what I'm actually looking for. And that's a problem. Okay. Fortunately, people smarter than me figured this out, and the hack was pretty simple. All we do, instead of taking that sum of squares and divide it by the number of people in our sample, we just divide it by the number of people minus 1. Okay. And if you're an algebra whiz, Basha, what happens when I take some value and I divide it by one number and I divide it by a smaller number? What happens in my outcome when I divide it by a smaller number? I divide it by a smaller number.
Oh, it gets bigger.
It gets bigger, right? Again, looking at these formulas and thinking about exactly what's happening here, right? I'm reducing the denominator by 1. If my denominator is smaller, what happens to my output? It gets bigger, right? And so this, and I don't understand the mathematical properties of the theory behind it, but this produces an unbiased estimate of our population variability, okay? But if we think about this, Josiah, if I have a very large sample, like a really large sample, to what extent is my sample statistic likely to be biased relative to the population parameter? Less so. What if I have a really small sample? More so. Okay. Let's say if I'm looking at this formula, if let's say I calculate, let's say I capture 500 people in my sample, and I divide whatever that numerator is by 499 instead of 500, what does that do to my outcome?
It makes it bigger, but not by a lot.
But not by a lot. What if I have 10 people? Makes a big adjustment, right? And so if we look at sort of what's going on in these formulas, we can understand exactly what's happening with this. For my smaller samples, I need a bigger adjustment. And so with a small sample, subtracting 1 is a larger proportion of your total sample then, and so you get a bigger adjustment if I get very, very large samples. And this is where we, again, with some large sample statistics and so like SEM types of stuff, look at most output, they were working with Z values and stuff like that, because they're just assuming, hey, if you're doing this, you should have samples that are big enough that we don't have to worry about this type of bias and just working forward with that, right? But again, just even looking at this formula, we can start to see, yeah, I see how that works. It's not magical. It doesn't require linear algebra to go through and figure out in theoretical numbers that say, just change in the denominator. The denominator gets smaller, my output gets bigger, right? We'll see a lot of this stuff as we move forward. Yeah.
So just to clarify, so for like a really large sample, you don't need to subtract 1.
Nope, you always will, just because that's how it always works. But there's kind of a digression for if you start to get into different programs that are sort of large sample estimators and things like that, you'll see people start to become less concerned about this type of stuff.
Okay.
Yeah.
That sounds good.
So let's say we go through and let's say we now have a set of 5 scores. It's not our population. It's not everybody. It's our sample. Okay. Step one, we're going to do the same thing. We're still going to calculate deviation scores. Step two, same thing. We're still going to square each of those deviation scores. Step three, we're still going to sum all those deviation scores. At this point, nothing has changed. The only thing that changes is now when we go through and we calculate our variance, our sample variance is going to be our sum of squares divided by the number of people in our sample minus one. So we get that adjustment and then take the square root of our sample variance to get our sample standard deviation. So it's just that small adjustment. Now in a sample of 5, this is going to be a pretty noticeable adjustment in terms of increasing the variability in our estimate of population variability. As we start to get larger and larger samples, that correction is going to be systematically less. So again, computation for sum of squares is the same. Is the calculation of sum of squares for your sample, and your for a sample statistic population statistic is identical. It's just only thing that we're doing is just making that small adjustment when we divide to get our value for variance. Questions on any of this? All right, cool. So population versus sample variability. We see here we got population, sample, variance. We see an increase when we jump to our sample, standard deviation, corresponding increase. Formulas there, just kind of bring it all together in sort of one place. All right. So we always start with variance. We're calculating our variance, and then once we have our variance, we can go through and calculate our standard deviation. Again, the standard deviation is reporting your variability by, again, talking about distance from the mean. In any type of distribution, some people are going to be close to the mean. Most people should be close to the mean, but some people are going to be farther and farther away as we start to get out on those tails. But if I know both the mean and standard deviation of a distribution, assuming that we have some sort of general understanding that it's probably something that's following some sort of natural or normal curve, what I can start to do is I can start to make some inferences about the likelihood of a score. Okay. If I'm looking on a normal curve, right, and this is going back to sort of undergrad statistics, right, we know that there are certain marks on this normal curve where we see anything that's variables falling along a normal curve, a little over 2/3 of the sample of scores are going to fall between standard deviation above or below. Okay, if we go out to 2 standard deviations, again with a nice normal curve, we're expecting 95% of scores to fall between 2 standard deviations above and below. If we go out to 3 standard deviations, over 99% is going to fall between 3 standard deviations, right? So what I can do with this is I can start to take information and start to, assuming that I that whatever I'm measuring probably approximates some sort of a normal curve, I can start to make inferences about magnitude based on means and standard deviations. Okay, so let's say we've got height of adult males. So I don't know, I pulled this on Wikipedia or something like that. Say average height 5'10", standard deviation 3. Okay. So Amanda, if I said, hey, I have an adult male in the U.S. behind my back. How tall is this guy? What are you gonna guess? 5'10". On average, how wrong are you think you're going to be? 3 inches, right? But what I can do is I can start to bring in guys. And I say, all right, here's David. David's 5'6". Assuming that height occurs on a normal distribution, is David? How short is David? A little more than the standard deviation below, right? So David's maybe a little shorter, but he's not incredibly small. Right? And then we got John. John is 6'6". What do you think, Basha? Is John inordinately tall? Yeah. John's over 2 standard deviations above the mean, right? These are the dudes that make me uncomfortable. Like, so I'm 6'3". Sometimes, like, if I have to like look up, it's like it weirds me out. It's not something that happens a lot, right? So yeah, John's a freak. He needs to go home and stop scaring people. Then we look at Matthew. All right, Matthew's 5'2". Is Matthew small? Yeah. Matthew is over a couple standard deviations below the mean, right? And so we can go through and start to say, are these scores extreme or not? And so this is kind of a fun example, but it's not sort of really meaningful in that, or it really doesn't punch, because height is the thing. Like I can look and say like, okay, that guy's 5'6", that guy's 6'6", this guy's 5'2". I understand because I live in a world and I sort of understand something about height, right? But what if we go through and we say, all right, I've got this measure of extroversion, right? And the mean is 85, the standard deviation is 20, right? If I just say, hey, so-and-so scoring this extroversion measure is 120, Teresa, does that tell me, absent that mean and standard deviation, do I know anything about anything with that? Yeah, it's a meaningless number. It contains no informational value, right? You can say it was, I don't know, Bert might as well have a score of 5 billion. I don't know if that's big or not, right? And for you clinical folks, this starts to become an important thing when we're thinking about measures, right? I'm a big fan of when you're writing things up, say, you know, this is someone's score on random measure of whatever, right? But if you can go through and say, sort of, previous studies have found sort of mean standard deviation, average college population, right? It's like, then I at least know sort of relative to sort of where things are at, or clinical samples have found mean standard deviation to be XX. Now, all of a sudden, that gives me information where I can start to gauge sort of like the severity of that score relative to other stuff, right? And so here, I have a mean of 85 and a standard deviation of 20. How's Bert? Bert's high-ish, right? Under 2 standard deviations. Is that right? Yeah. But he's still sort of starting to hit sort of the high end of things. Leon, over 2 standard deviations. Reynolds starts to be pretty low, right? And so information about mean and standard deviation starts to be able, we can use that to sort of place individual scores and sort of they're likely not exactly where they're at. Because again, all this assumes sort of some natural normal curve with stuff, but at least gives me a sense of magnitude more so than just some value in and independent of itself. Questions? Next week, we're going to take this concept and sort of step it further into actually talking about Z-scores and things along those lines. That sort of makes this a little bit more formalized. So thinking about our standard deviation and inferential statistics, our inferential statistics, these are anything with a p-value. This is stuff that's the goal is trying to help us differentiate signal from noise. Okay? Are these things that I see, are these likely to be real things that are representative of differences, associations in the population of interest, or is this just static, right? Is this just random fluctuations, okay? And what happens as we start to think about how variability impacts this, it's a lot easier to see patterns in data with low variability. If I have data that have high variability, it starts to become a lot harder to kind of tease things out, right? So I've got 2 experiments. I've got experiment A and experiment B, okay? Which one of these experiments is it easier to see systematic differences across these groups? What do you think, Sam?
I would say, but the way you left the question is.
Sure. Okay. So if we're looking at some of these, right? If we're sort of kind of eyeballing stuff, what do you say? What are you seeing is the difference between A and B here? Mm-hmm. Yep. We're getting a lot more variability in experiment B than experiment A, right? And so if I go through and I plot out these 2 groups in experiment A, am I seeing differences between groups 1 and 2?
A little bit, yeah.
A little bit. Actually, quite a bit. If we look at this, or where those tails are sort of going through, these are non-overlapping distributions. When we superimpose that natural curve, that normal curve on there, we get very little overlap, right? And we can go through and we can say, well, we know that we have a mean difference of 5 units, but it looks like group 1 and group 2 are very different from one another. They're very clean, right? We don't have much variability within these, right? So going back to that idea of variability is error. For these two groups, if I guess the mean, how close am I in sort of guessing the likely value of any individual score? Probably pretty tight and pretty close. I don't have a lot of, I have very discrete homogeneous groups, right? If we're thinking about from you experimental folks, right? If I have a manipulation that does this to groups, this is beautiful, right? This is something that's accounting for a huge portion of variability in whatever it is that I'm measuring, because I have people sort of have this manipulation or not, and it really tightens them up. Whatever I'm measuring is hugely dependent on this, because the score that I'm getting is has very little variability, okay? What about this? Just as a comparison, Sam, if I go through and look this, is it easy to see differences between these two groups? No, it's all over the place, right? Everybody's on top of one another. My two distributions are hugely overlapping with one another. And it starts, still, we have the same mean difference between these two groups. It's still 5 units, right? But that's a lot easier to see than that. Here we have more variability. We have noise, right? If we're saying, oh, if I guess the mean for either one of these groups, how confident am I that some randomly selected person is going to have that value or something close? Not confident at all, right? Because they're kind of all over the place. And so this is what we're trying to do with our inferential statistics, is tease out the difference from the noise and say, what evidence do I have that this is likely something that represents sort of true difference or association in the population versus something that could be just variability and static based on the data that I'm collecting and the methods and so on and so forth. Okay. Kind of see sort of how this plays in and ties together. So characteristics of our standard deviation. Adding or subtracting constant from each score in a distribution doesn't change the standard deviation, right? So if I add 5 to every value in the set, and my standard deviation is 3, standard deviation is still 3. I've just taken that distribution, shifted it around, but it hasn't changed at all positioning of the scores. But if I multiply or divide each score in a distribution by a constant, that's the standard deviation is going to change by that same number, right? And so, yeah, if we think about Christina's some scores from the RSE as, instead of taking the mean, think about her as adding those scores, but we can also take, so that we can think about that scoring as taking each one of those scores, dividing them by 10, and then adding those up. Technically, what she's done in creating the sum is added a scale divided by 10. So we should be able to recover standard deviation of that distribution by dividing it by 10, right? So we should be okay there. So just understanding this relationship, because a lot of what happens in applied statistics is taking what someone's reported and then trying to back translate and figure out the thing that I actually want to know versus the thing. It's not saying that they necessarily did anything wrong. It's just the thing that I want from that study might not be what they wanted to do. My goal as an author is to provide you with as much information. Like, I'm going to tell you the analyses that I did, because this is why I wrote the paper, but I can understand that other people may want it for different things. So here, mean, standard deviation, sample sizes, stuff like that. So if you need to go back through and reconstruct stuff, here you go, because trying to track people down to get sample sizes and means and standard deviations is a headache. So thinking about factors that influence our variability are extreme scores, range, variance, everything. If I start to get very, very extreme scores, stuff that's hanging out on the margins, that's going to increase and start to impact my variability. Okay. Sample size. We see that range increases with sample size, but our variance and our standard deviation remain fairly unaffected. Why is this? Why does this make sense? It's the average distance from the mean, right? We have that correction. So as my sample size gets bigger and bigger, I'm going to have less and less of a correction. So that should stay pretty stable. Why does my range start to increase with sample size? Yeah. As I start to get more and more people, the likelihood of me capturing some of those people who are out on the fringe, some of those extreme values starts to increase, right? And so that's the thing. If I have a really big sample, I shouldn't be freaking out that I find sort of more extreme values, because that just tells me I'm doing what I'm supposed to, what should happen. And if I've got that really big sample, am I too concerned about really extreme values? No, because they're going to be watered down by this stuff, right? So again, this is where people's take this hard and fast rule, oh, anything above sort of this value is that's an outlier and I'm gonna kick it out. I'm gonna encourage you against using the word outlier. Think about the extreme values. Outlier connotates something. Extreme values is saying like, hey, it's just a big value, right? Now this may be something that needs to be addressed, maybe not. It really depends on the situation, what I'm measuring, what I'm trying to do, right? But knowing that as I start to increase, if I start to get some of those people on the fringes, that just makes sense. It just tells me I'm doing good science. Em, did you have a question?
So would it be accurate to say that's like a function of?
Yeah. Yep. If I play the lottery, if I play, 100 lottery tickets every day or every sort of week, I don't know, play the lottery, however often that comes out for my entire lifetime, the likelihood of me actually catching a jackpot starts to become much better if I sort of buy 5 tickets over the course of my lifetime, right? So just recognizing that and you're like, oh, this is just something that's going to happen. Now, if we start to get extreme values in small samples, can we get extreme values in small samples? Oh, sure, right? Sometimes it just hit the jackpot, get someone who's way out of bounds, right? Like the first person I sample through Prexis is like 7.2, and I'm like, yikes. I was only going to catch sort of get a sample at 20, and now this person's going to swing it way off, right? So it can happen, but on average, these smaller samples are more likely to catch just those folks in the center because there's more of them. Okay. Stability, we see that range fluctuates unpredictably. Standard deviation variance stays pretty much the same, and then in open-ended distributions, we just can't calculate range, standard deviation, variance in some of those sensor data, and that sort of it's open-ended distributions. They're not useful things, or they're not things that we can actually kind of do. So what we end up doing is probably those interquartile range, things along those lines. Or if we just say, hey, I recognize that the top value of my scale is an indefinite value, but I'm just going to ignore that, pretend that it's just the top of the scale, and just run this as a 0 to 10 scale as opposed to corresponding to actual physical values. Maybe you do that. I would just say in general, as you're planning stuff, just be careful about that open-ended top scale. It doesn't come up too much, but I'm thinking things like income, right? We say X and above. It's a big space that so people falling in that category could be orders of magnitude different, right? All right. Think about final statistics that are capturing shape of our distributions. Symmetrical distribution just refers to any type of distribution that's the same on one side roughly than it is as it is on the other. So here is our normal curve, but we can also have non-normal distributions that are symmetrical, right? If we get a nice bimodal, multimodal distribution, it's still symmetrical. It's just we kind of have kind of 2 distributions that are looking like they're not going on here. We can also have symmetrical distributions that are non-normal in other ways, right? How would we describe, Matt, how would you describe this distribution here?
Uniform.
It's a uniform or square distribution, right? So everything on values are all the same, right? So it is symmetrical. Sometimes it's going to be a problematic distribution, sometimes it's not. It kind of depends on what we're doing. But this is, actually, and we'll get into this next semester, burn this into your brain as an example of a fixed effects assumption, okay? Where all values in sort of my range are equally sampled, right? It's not saying a normal distribution. It's actually a very much non-normal distribution. But again, just showing the types of things that can come up. And this is the thing, I'm gonna have you in screenings looking at a lot of distributions and describing these distributions. It's going to be hard at first. It'll get easier as you go through because it just takes a lot of like time just looking at different distributions and different data and what things look in applied analyses. At first you can be like, oh, wow, that's the worst. I'm like, no, that's just what real data look like, right? It's not airbrush data, right? It's not People magazine data. It's sort of the data there with sort of all the hiccups and stuff like that that it usually has. But want to be able to differentiate the stuff that's sort of potentially concerning versus stuff that's just normal data.
Just saying that was an example.
ignore that. Like that, yet don't worry about it. That's not anything that's going to even come into like, so maybe halfway through next semester. So, but that was just a thing that I thought in my head. So don't worry about it. Okay. All right. So other statistics that help to qualify shapes of distributions. I can talk about skew. Skew is technically your third population moment. So mean is your first population moment. By moments, we're just talking about characteristics, right? Mean is the first characteristic, variance is the second, skew is the third, and it just describes the symmetry, okay? If a positive skew, okay, this is where people sometimes get sort of turned around. Positive skew, skew depends on the tail. That's the interesting thing about a skewed distribution is the tail. Positive skew, tail's going in the extent of higher direct values. Negative skew, tail extends towards lower values here, okay? And so we see here, as we've talked about, that mean no longer ends up being a valid measure of central tendency when we start to have very skewed distributions. And things order up very nice and neat. Mean is always going to be dragged out farthest towards the tail. The mode is going to be on the opposite side towards where the majority of the distribution is. Median is going to be somewhere in between the mean and the mode. And so this is why for skewed distributions that are noticeably skewed or very skewed, median is probably a better measure of central tendency than median is probably a better measure of central tendency than the mean is. Okay, kurtosis, this is your fourth population moment or your fourth characteristic that we can use to describe a distribution. Kurtosis describes the shoulders at the peak of the distribution. I have a fantastic psych methods article on kurtosis. If you want to do a deep dive into kurtosis and sort of the confusion, I'll forward it to you. It's probably not worth sort of reading and assigning for class, but if you're really into kurtosis, I can sort of send that your way. Essentially, what you need to know, just thinking about kurtosis is identifying the shoulders and peak of distribution. If we have a positive kurtosis, leptokurtic, okay, this is going to have heavy tails and a narrow peak. It's the stuff we see this. They go, it's normal. Well, it's not actually normal. We just got positive kurtosis because we're kind of peaked up here, and then these tails get kind of flat and thick out on the side. Negative kurtosis, this is platykurtic. We have sort of a kind of a round, kind of a hump distribution where we've got not a clear peak, we've got flat and centered, heavy shoulders. It's kind of this stumpy distribution. Okay, you don't need to worry about leptokurtic, platykurtic unless you want to sound fancy. So talking about this as positive, negative kurtosis, but just understanding what these distributions, what this means in terms of thinking about what these distributions look like. Okay. What we see is the kurtotic distributions tend to underestimate our population variance. Okay. It's easy to kind of see with the negative kurtosis how that might underestimate our population variance. Can someone tell me why positive kurtosis underestimates our population variance? Yeah. So say a little bit more about that. So in the negative kurtosis, what are we missing in negative kurtosis?
Well, and you don't really have like the end tails.
Yeah. So we're missing the tails. We're missing the extreme folks here. What about positive kurtosis though? What are we missing there?
Like that top middle.
Yeah, we're kind of missing the shoulders, right? I mean, so those aren't as it's easy to see, oh, I'm missing the real extreme values. But really, if I'm looking at what's happening, so the majority of the distribution is kind of should be hanging out right here, right? But they're not. I'm missing those folks, and everybody's kind of centered up towards that middle piece, and it's underestimating my variance, right? So our concern with kurtosis is that we're underestimating population population variance. And so what this can do is it can start to bias our standard errors, our estimates, and things along those lines. Now, as my sample sizes start to get bigger and bigger, my concern with this gets less and less, but sort of noting that my concern is with the highly kurtotic distribution, then I'm going to be underestimating variability and potentially introducing bias into my estimates of that population parameter that I don't know, but I'm trying to make a guess at it with my sample. And if I'm starting to see this, I might start to worry about potential biases here. Questions?
Can you give me an example of like when this might happen, like either positive or negative? Oh.
That's one, right? That flat distribution, right? I mean, that's a horribly negative kurtotic, and you'll see like the indices of that you'll get is like, oh, it's super kurtotic, right? And that in the negative direction that I don't have tails or a peak or anything. We got that kind of square uniform distribution. This is an example. Or a lot of times if I get something that's kind of skewed, right? So I kind of have everybody's kind of lined up around 0, and then I kind of have like kind of a skewed distribution to go out. You get a high value of skew, but you usually get a high value kurtosis for that because you don't have a shoulder, you've got a too narrow of a peak on that as well, right? So, and we'll see lots of examples where it's like, okay, it's kind of normal, so we've got some positive kurtosis and that we kind of got everybody kind of lining up, and then things kind of flatten out from there.
So follow up on that. So can sometimes like positive curiosis like be good? So like if you're looking at, I'm going to use substances because that's like what I'm most familiar with, but if you're looking at like tobacco in high school students and you see like the positive kurtosis is mostly like around the 1 and the 0. And
Yep.
then you have like these outliers, like 3 and 4 for like their scores of like how many times they consumed like tobacco within the past month. Could that sometimes be a good thing?
Well, what we need to be thinking about here is the extent to which our distribution that we're seeing reflects the phenomena of interest, right? Do we expect high school tobacco use to be a normally distributed in the population? Probably not, right? Because a normal distribution says you have sort of most people have some people have none. It's sort of like very, very few people have none, and very, very few people have a ton, but it's sort of this distribution here. This only starts to become a biased distribution if we're assuming that the thing that we're trying to capture is normal, right? And so in your case, you might be less concerned about, we still might be concerned about whether or not this distribution and the extreme values are going to start dragging things around. We're probably going to be less concerned about underrepresenting the variability of the population, because probably this thing that we're seeing is probably actually reflective of the actual phenomena of interest. But if we think that the thing that we're measuring should be pretty normally distributed, and we're seeing sort of strong positive kurtosis where everybody's kind of like stacked up in the middle, and then we only have, then I might start to worry about sort of that variability issue, unless I start getting enough people in the sample, and then I'm like, okay, then I'm probably okay with things. Okay. So again, always thinking about what am I seeing and what would I expect to see in the population if I had all members of the people who I'm interested in studying, like the whole population. Would I expect this to be normally distributed? A lot of things probably, but a lot of things not, right? And so just thinking about that in terms of representativeness.
So, I wanted to do this question for an example, just to make sure that my understanding. So say we're going back to the height of purchases.
Uh-huh.
So the positive, because we have a lot of the tail,
Uh-huh.
would that be like saying that we have a lot of short people, a lot of really tall people, but not as many in the middle? Comparatively for the negative, there's a whole bunch of that not really in the tails. Is that kind of saying that everybody's centered around the average height, but not really short and tall? And then also for like the flat one, would that be like everybody is the same height? Is that kind of?
Right on everything except the last one where everybody's the same height. Because if everybody's the same height, then we just have one bar of where everybody is at, right? What we're saying is if I, let's think about that flat distribution as colors of marbles in a jar. That's not a great example because that's a nominal variable. But if I went through and I have marbles in a jar and I put 10 marbles of 7 different colors in there, then I know that each color is represented an equal amount of time. Then it's kind of that that square distribution, right? So let's say I'm looking at I thought about weight and then I thought like, what, that's not a good, but like, let's say wrestling, right? Or boxing, or it's like some sort of weight-based competition sport, right? We have an equal number of people at this weight, an equal number of people at this weight, an equal number of people at this weight, equal number of people at this weight. We got equal representation at each weight class, right? Versus weight that we might sample from sort of the normal public that would be normally distributed, right? So again, this is generally most problematic if we've got very small samples. As we start to get larger and larger samples, it starts to become less of an issue. So this is more about describing kind of the characteristics of our sample, and then just noting if things start to get really crazy or we have really small samples, then we start to become concerned about it. Cool. All right. Statistical indices of skew and kurtosis. These are garbage. Well, they're not garbage. They're useful things as long as they're used appropriately. Okay. So we have metrics to measure skew and kurtosis. Again, also another interesting differences in how you can go through and calculate it. We have sort of metrics that will give us a number for skew and kurtosis. The problem is that any formal tests of significance are usually not worth looking at, right? So I will go through and look at a distribution and we'll say, here's your value for skew, here's your value for kurtosis, and there'll be a p-value there that tells me that whether or not it's significant, okay? Anybody want to go on? What does it mean if I find that something is statistically significant? Almost always. What does that mean, literally? That's how we often interpret it, but that's actually, yeah. So like mathematically, if I find that something's statistically significant, what does it often mean? Okay, well, yeah, if we use that cutoff, sure. What is our null hypothesis? If we think about hypothesis testing, what's almost always our null hypothesis? That something is equal to what? What, Teresa, did you say? Yeah, 0. And literally what our statistical tests tell us whether or not something is likely equal to 0 in the population. Okay. Like literally that's what like something is. So we're testing against a null hypothesis, right? And so yes, is sort of likely they're sort of based on the data that we've collected. These data are quite unlikely if the population value of this thing was 0, right? And we have cut points for statistical significance. If we say less than 0.05, which is kind of a semi-arbitrary, then we say, okay, we would call that statistically significant, although we're trying to use different language here just for exercise. But basically, all this is telling me is that my skew or my kurtosis value is not likely not to be 0. As my sample gets really, really big, what happens to the sensitivity of my statistical tests? Starts to get easier and easier to call things, say that things are likely not exactly 0, right? So if we're using good powered samples, right, and I find that I have significant skew or significant kurtosis, what does that literally tell me?
Representation of population.
Well, going back through, remember that almost all statistical tests are just telling us that something is likely not 0, right? So basically all that skew is telling us that significance value for that skew, sure, I have significant skew, but all that is saying is that my skew value is likely not 0 in the population, or my kurtosis value is likely not 0 in the population. And maybe not have any reason to know this, we haven't got there yet. No one assumes that anybody's data has skew value of 0 or kurtosis value of 0. No one cares about that. That's not an assumption of your data, right? And so if I've got a sample of 500 and I say, oh, I have significant skew because I looked at that p-value and started doing a bunch of weird ass transformations on my data because I have significant skew, you just made things infinitely more complicated for yourself for a non-issue, right? And so always being careful when we're looking at these p-values and these significant values, recognizing that all these are doing is literally saying is based on the evidence that I've gathered, assuming that these data came from a population where the value was 0, these data would be unlikely to have occurred, right? Which we'll get into later, how that's kind of all backwards and things like that. But basically boils down to, it's unlikely that this value is 0 in the population if we accept the sort of premises of the process. But what we need to do is ask ourselves, do I care if it's 0? Does it matter to me if it's 0? What does it mean if it's 0 or not? Like, is this something that's useful for me to sort of go through and do my thing, right? And so this is where a lot of people get sidetracked, right? Because I identify that p-value on the skew, back, oh, I got a significant skew or kurtosis. Now I need to go do a bunch of stuff. Almost always, no, you don't, particularly if you've got large samples. So what we're going to look at and pay more attention to is the absolute value of those indices, and then try and make some decisions that, hey, is it starting to get large enough to a point where I start to become worried about stuff? Okay. In general, rule of thumb for problematic violations of normality, some you'll see like 2, right? If I got skew or kurtosis values larger than an absolute value 2, so higher than negative or lower than -2, higher than +2, as potential deviations from normality. But remember that these violations exist on a continuum. Again, if I could sort of sink anything into your brain right now that would never go away, which is a terrifying thought. Don't have that. That would be too much responsibility to have. But the fact that sort of with this stuff, what we're working with always are things that will exist on a continuum. Okay. And so if we start saying like, oh, my data are near normal because it's got a skew value of 1.96, that's not true. That's going to have a significant skew if you look at those data. Or my data are problematic and I need a transformation because my skew value is 2.05. The distributions are functionally identical. There's not a difference. There's nothing magical that happens at that thing. At that cut point, what we want to do is be thinking about on a continuum, where does my data fall? Given the sample size, what I'm measuring, is this expected? Is this something that's going to be problematic for my analyses? And using this flexibly to go through and think about sort of what type of action do I take? What decisions do I make? And Sam, your decision at one point could be different than Emily's decision, right? And both could be equally defensible. Hopefully what we would find that we would get roughly the same, arrive at the same conclusion based on what you've done. If we don't, then we start to worry about sort of replicability and generalizability and sort of things along those lines. But these are things that we want to be keeping in mind as we're moving forward. So that bright line stuff gets us in way more, it's comfortable, right? We love to put things in boxes and I want to know, hey, what's the decision point? If I do this, am I right? And if I don't do it, it's wrong. We've reached a level that's beyond that now, where you're at in a doctoral program where we got to let go of those arm floaties, and you got to sort of think about things in context and start to make decisions about sort of the best way forward, weighing out pros and cons. Okay. So we will use sort of these and sort of saying, okay, this is generally what we would talk about in terms of a benchmark. So it's just not complete anarchy, but always wanting to say it's not just because this is significant or problematic or anything along those lines. Okay. And we'll get a lot of examples of working through data and sort of have opportunities to talk about in class. Again, the thing to remember too is big samples fix a lot of stuff, so long as they're not problems with the selection, but big samples make things a lot easier. In addition to having more power, things get a lot more stable, and we have to be less concerned about stuff as our sample sizes get larger and larger. So it's nice to be able to do that, invest in that if you're able. Okay. So again, please do not, I will get very crabby with you if you just say like, oh, this is problematic because the value was over 2. You know, that's not what I want you to be doing. I want you to be thinking about things in context and sort of what's the question I'm asking? How does this all play in? Oh, because Tara will judge you if you use benchmarks as bright line justifications. That's my wife, Tara. We're in Scotland, and she doesn't. I like showing that picture. She doesn't like it, but she doesn't like the news with whatever was going on at the point in time. Okay, outliers, extreme values. Univariate outlier. This is some variable that just has a very, very large, very, very small value. We will identify extreme values empirically, and we'll say, oh, this seems to be an extreme value. But what's more important is figuring out why that score is an extreme value. What's going on with it, okay? And anytime I see an extreme value, there's a number of possibilities that pop into my mind immediately. One, someone screwed up the data entry. Like someone just punched in the wrong number, someone double keyed something. Always want to go back through, and this is why it's always good in running your studies, having sort of a hard copy. Now, what's nice about a lot of stuff we've converted to electronic form, so there's not sort of paper pencil measures that people then have to go through and enter and sort of that whole thing. So that's nice. That cuts out some of this, but always want to say, did someone sort of walk by? Did my cat step on the keyboard? Like, is this a real value, right? So always going through taking a look at this. Talked about the missing data codes. I do this all the time, get a ridiculous value for age. My sort of average age of my college student sample is 44. I'm like, that doesn't seem right. Go through and it's a couple 999 codes that's dragging that out. Case is not a member of the intended population of study. Example we gave about finding my undergraduate who's making 125 G's. Like, whoa, yikes, is this person someone who I really want to study? Nope, it's someone who I captured, but they're not part of my population of interest. And if that's the case, then we can go through and let that person exclude that person without too much concern. Case is a member of the intended population, but my variability underestimated by the sample. So I'm sort of go through and I say, got a small sample of looking at substance use or something like that. I get 20 folks, and most people it's 0, 0, 0, 0 something, and then I get someone who's like a daily user, and that person is way the hell out there, right? That's not to say this person is weird. This is actually someone who I want to capture, but it just everybody else reported 0, and so now this person is way far away from the rest of the distribution. So wanting to think about how I go through and address that stuff. Okay, these extreme values, particularly in small samples, can start to wreak havoc on your inferences, start to impact sort of our coefficients. And again, these are always numbers that I'm using that are saying this is my best guess about what's happening in the population. And as soon as I have a small sample and I start to get weird values in cases, it can start to drag that all over the place. I get inflation of type 1 and type 2 errors, starts to impact the generalizability of my solution, which is what we should always be concerned with our research. And so these things can start to play tricks on us. Tricky thing is sometimes we like the tricks that they're playing on us because it makes my samples or my groups different, or it sort of gives me a really nice correlation if I've got, we got X and Y, right? I've got kind of a cloud here and something out there. That correlation looks like this. That point looks like that. I'm only a human being. I'm going to be tempted to think, oh, well, make some sort of justification for keeping that person in there. But absent that point, this whole thing collapses, right? And that's probably a restricted range issue in there. But I need to decide sort of what can I do with that situation. So sometimes we often think about like, oh, I did this outlier is screwing over my stuff. But a lot of times is doing the other thing. It's making, and if I'm not terribly on the up and up, and I'm not sort of reporting that or acknowledging that or addressing that in the analyses, so I can start to maybe publish something that no one in their lifetime will ever replicate again. Because what we didn't know is that, so-and-so in 68 had a handful of weirdos in their sample that sort of drove the whole finding, right? And so sort of wanting to think about research ethics in that situation. Other thing we need to think about are extreme values, outliers in our categorical data. We don't think about this a whole lot, right? But if I have a dichotomous indicator with a very, very unequal splits, essentially what I've got is what I have is outliers in a dichotomous variable, right? And so what happens is that smaller category starts to have any individual in that smaller category has a much, much larger influence on the whole sort of analyses than sort of the average person in the larger group. This can start to attenuate associations. Things start to look weird if I don't have equal representation. And what we need to do when we have these unequal splits, we need to start asking ourselves, is it essential to have this variable in my analyses? Hopefully, in the research planning phase, before you run your study, you would think about, like, can I capture sort of these folks, sort of my intended group, with these analyses, and sort of plan to sort of address that on the front end, right? So let's say, Teresa, hopefully, like, you're looking at, want to look at autism and trauma, right? That hopefully you wouldn't just get a trauma sample and then just hope some people had autism in it, because that's not going to work for you, right? You're going to have, like, oh, I've got a group of 3 versus 70, right? And I can't do much with that, okay? Where does this really come into play? Think about categorical variables where we don't have proper representation of folks. Diversity issues in our group, right? Our samples are predominantly white, and sort of then if we sit in, and so what we do is we're like, oh, we're trying to make up for it by saying, like, oh, well, you're white, non-Hispanic, or everybody else. Well, now I've got a nonsensical comparison group that doesn't have any interpretive value. But if I start trying to sort of cut things out, now I don't have enough people to do things. And if I do try and run those analyses, I get weird stuff, or stuff doesn't show up, and things along those lines, right? And we're kind of caught too, because I'd like to think we're trying to sort of go through and capture things, but we also don't want to misrepresent sort of findings and say, oh, sort of this group is different than that group, based on sort of a weird value that doesn't sort of match up and actually map on to probably what's going on in the population, right? So always sort of remembering that we can experimental folks, it's often not an issue, because if I'm running a study where I'm randomly assigning people to groups, hopefully if I got a weird randomization schedule where 95% of my people got randomized to one group or someone else, he's like, oh, whoops, I'm going to run that randomization button again to sort of fix that, right? But just recognizing that this is something that can come up. Oftentimes with continuous variables, we'll go through ahead and calculate z-scores. Z-scores are equal to standard deviations from the mean, right? And so what we will do is start saying, you know, if I've got a reasonably large sample, anything more than 3.5 or 3.3 standard deviations above or below the mean start to become pretty extreme values. But again, if we've got lots of people in the sample, that starts to become less problematic. If I've got 20 people in my sample, I get a z-score of 4 for somebody, then maybe I'm worried about that. So we can use these standardized scores to start to evaluate and identify potential cases that might be potentially problematic. But like anything else, we want to be very careful that we're not just applying bright line cut points to people, and always supplementing with graphical methods. What I don't want to do is just run z-scores, find these are the cases that are above or below a certain value of my preference, and then just start throwing people out. Always graph those data, take a look, see what's going on with that, try and understand your distribution, what's happening. Got our bar graphs. So these are nice for categorical data, mean differences, things along those lines. These are cool. Histograms. These are most often how we go through and present our continuous scores. Everybody's kind of familiar with histograms. These are frequency distributions. Here we've got CAP scores pre-treatment for some data that I have. So we've got a skew of -0.36 and kurtosis of -0.79. Do we like that first distribution with the CAPS data? Anybody not like it? No one will be baited into having an opinion. That looks pretty good. I mean, there's really not that many. There's not that many people in that group, right? It's a small sample. That's pretty good in terms of looking at sort of actual. I mean, it's not nice normal stuff, but that's what distributions look like. This other one, right? Now all of a sudden we've got sort of a much stronger skew there, skew of 2.4. Kurtosis is 6.8. Remember when I talked about how those skewed distributions can start to have really intense kurtosis? Again, because it's looking at that peak, right? And then everything going out from there. Here we're looking at ordinal angular scores. Most people are 0, and then people start to scan out. But it's nice to see what this is looking like, as opposed to just looking at skew and kurtosis values and then just determining back, oh, this is problematic. Not if I actually look at the distribution, I can say, okay, I can see what's going on. This was an experimental manipulation. Did people get angry with this? By and large, no. Some people did, but needed to determine sort of what I want to do with this data and how I want to go through and analyze it. All right. Last thing we'll talk about are box plots. I've been promising box plots, and so we've saved the best for last here. Box plots, pretty straightforward. Again, these are median-based statistics. The midline of your box plot, this is just the median. Okay, this is the median value of your distribution. The bounds of the box, this is going to be your first and your third quartile. The box covers your interquartile range. Okay, so again, so if I've got a normal distribution, this sort of middle 50 here it's 50%, but this should be, this is capturing by definition where half of your sample is falling. Your whiskers or your inner fence, got to be careful because this can be two different things. One, this could be your minimum and maximum values. Okay, so your whiskers will go out to your minimum and maximum values. Or if I have cases where there are extreme values, those whiskers are going to get to the point of the most extreme value that still is within 1.5 times the interquartile range. Okay, so here's your interquartile range. These values are either going to be the min or the max, or if we take this distance and we take 1.5 times that, it's going to be the score that's at least the most extreme score that's within that 1.5 times the interquartile range. Okay. And then if we have extreme values, these are going to be in SPSS indicated by asterisks that are extending beyond the whiskers. In SPSS, you'll have open points. If something starts to get beyond 3 times the interquartile range, those will show up as asterisks. So you have circles and asterisks. The circles are things that are still within 3 times the interquartile range, but beyond 1.5. The asterisks are going to be things that are beyond 3 times the interquartile range. Okay, so again, in a normal distribution, we would expect that 95% of your data should be falling between the whiskers. If you've got a nice normal set, most of your stuff should follow there. But again, this is assuming a normal distribution, which oftentimes our stuff isn't. Okay, so like right here, let's say we've got 4 conditions, and we're looking at positive affect across these conditions. Josiah, what are you seeing in this example here?
Looks like all 4 conditions are pretty similar, but the 4th one definitely has outliers. The median is pretty similar across the outliers seem like they go or the whiskers are a little bit to the lower end.
Yeah, right. Perfect. Looking at here, median values all pretty much the same. I mean, there's some variability, but it's not really all that much. Sort of the real range. So for condition 1, 2, and 3, the upper and lower whisker is just the most extreme value in that condition. And those are all range is looking pretty similar. When we get to condition 4, it looks like there's something maybe a little bit different going on in that we have extreme values. These are values that have fallen beyond 1.5 times the interquartile range, right? But they're not that far off, right? So we see the upper and lower whisker, those are values that represent the most extreme values that are still within 1.5 times the interquartile. And then we got the open circles that are capturing those ones that are extending beyond, right? But really, Josiah, if you looked at this, would you, and this was like an ANOVA-based analysis, would you have a strong hope that you would find differences across these groups? Probably not. Everything's looking pretty much the same, right? Right. What about this stuff? Teresa, what's happening here?
Your medians are a little bit different than your conditions.
Mm-hmm. What type of distribution are being represented by this set of box plots? Yeah, well, what would you expect if we were on a histogram with the distribution of each one of these conditions? What would you expect that histogram to look like?
All look skewed.
Yeah, it all look really skewed, right? So we have medians running across, we have interquartile range and things are looking, but what we're seeing is that people tend to score low, but when they don't, they're scared. We're seeing people out in the tails. Here, these are values that are falling within 3 times interquartile range, beyond 1.5 times, but still within 3. And then we got these asterisks out here. These are folks who are sort of beyond 3 times interquartile range. Okay. So again, just with this, can you start to go through and generate a lot of information about things that are happening in our data. Okay, so final thoughts. Again, a lot of people coming in thinking about statistics like, oh, these are the buttons I push, these are the pull down menus I click on. If I sort of hit this number and this threshold, then I'm going to do this. And that's, no one can argue with me about stuff. That's the wrong way to go through and think about things, right? There's a lot of context that you need to take in, a lot of decision points, a lot of weighing pros and cons of different things. Okay. And so Hal makes a nice point that always remember that statistics are not divorced from methods. They're one and the same. I can't fix, I don't have a statistical fix for garbage methods or things that I bungled or didn't think ahead of. And so I've collected data that are really kind of difficult. Once they're there, I can't, I'm limited in what we can do with that. I mean, we can work around stuff and say like, well, this is kind of the best we can do, but recognizing that our inferences that we pull from our statistical analyses are 100% and intractably tied to the methods that we use to collect those data. And if the methods are questionable, the whole thing is kind of out the window. We can have as big p-values as we want, we still can't infer much from them. Okay. And then remember, there are statistics, we're not their people. So I count for a lot of this stuff. You're in charge of your analyses and your decisions, and you are not beholden to bright line benchmarks or anything like that. So just remember that, think carefully as we're working through stuff. Okay. All right. That was fast and furious, and it was a lot of me talking. 2 minutes over. That's all right. Any questions before I turn you all loose?